Yes, good morning, everybody. Can you listen to me? Please raise your hand. Yes, very good. See, before we continue today, just a quick review of what we did yesterday. Everybody, good morning. Please settle down. Yeah, the strength is almost done. Yes, very good. Everyone is available now. That's really good. Now let us just do a quick review of what we did yesterday. We are still in basics and fundamentals. Okay. Just review of day 3, sir, what we did. Today we may close almost all the notations and fundamentals, mostly inclined towards DC steady state. Then we will start reduction techniques, which will be very, very interesting. But everyone should have a book or a pen, papers with you. And whenever I give problem, you need to attempt in front of me. And then we will discuss the solution, because we are going to start reduction techniques today. Okay, then what we did yesterday, we classified DC and AC. So what is DC supply? DC supply is unipolar, unidirectional, and there is no change in phase. Power frequency is ideally 0. It is used in small, independent, isolated power supply systems, and DC energy can be stored, that is batteries. Why DC is special even today? Because the systems driven by DC supply are precise, accurate, portable, compact, and easy in control. Ideal DC waveform look like this, whose ripple factor is 0. All applications like our toys, cell phones, wireless communications, laptop, PC, microprocessor, all comes under this DC because it is so simple and best waveform at signal level. So I also say DC waveform is the best waveform at signal level. So that is why electronic people like ideal DC. Okay, then I told you that here if you take the RL circuit, but for ideal DC steady state inductor acts like short circuit. So it is a pure DC current only flow. That is why there is no phase shift. And the right side is a waveform, which is a practical DC which have ripple. So practical DC have ripple factor. Ideal DC does not have ripple factor. Okay, that is the simple meaning. So practical DC waveforms have a lot of ripples. So we need to put filters, etc. But ideal DC waveform, which I told you, is not having any ripple. So in my subject, we do DC circuit analysis, but ideal DC. Then what about AC? AC supply systems are bipolar, bidirectional. There is a definite change in phase here, leading, lagging, such thing will occur, and power frequency is 50. They are used in large, bulk, continuously driven power supply systems, where electrical energy cannot be stored. Then where AC is number 1 in large power ratings, robust design, continuous duty cycle, high efficiency, there they are number 1. Ideal AC waveform is a sinusoid. Sinusoid means it can be either sine wave or cos wave. And ideal AC waveform total harmonic distortion is 0 because there is no harmonics. Because Fourier series of sin x is sin x only. Fourier series of cos x is cos x only. And applications is everything, our generation, transmission, distribution, utilization. So that is why sinusoid is number 1 waveform to transport, distribute, and utilize our energy at power level. So at signal level, AC is now DC is number 1. At power level, sinusoid is number 1. Okay. Then here I explained that in this case of an RL circuit, time varying flux will come, and that flux is responsible for phase shift between voltage and current. Here the impedance angle is 45 degrees. So current lags voltage by 45 degrees. Now this is another AC waveform, which is square waveform, but this is not ideal sinusoid. Now if you expand by Fourier series, lot of harmonics will come. Apart from fundamental component, lot of harmonics will come. So that is why total harmonic distortion exists. But for ideal AC, total harmonic distortion is 0. Then voltage definition. It is defined as the amount of work done in moving 1 unit positive charge from infinite distance to that point against the field. So it is the ability to drive charge. It is like a force which can drive charge. Units, range, and symbols. Then I give circuit symbols also. Okay, then I give circuit symbol, DC symbols, AC circuit symbols. Example of DC voltage sources, example of AC voltage sources. Then current. Current is rate of flow of charge. Okay, it is amount of charge transferred in given time. Units, range. Okay, then symbols and circuit symbols. Current sources have directions, voltage sources have polarity. Then example of current sources, DC series generator, BJT, feeder line in power system is AC current source, CSI drive. Of course, you will learn CSI is current source inverter. Then resistance. Resistance is linear time invariant property of matter, but resistance is a component to model and design this property. Then it is classified based on material like nichrome, tungsten, carbon, etc. Units, range, okay. Then Ohm's law, construction formula for resistance, okay. Then practical resistance depends upon temperature. Okay, practical resistance depends upon temperature, where RT is equal to R0 into 1 plus alpha T. And alpha is called temperature coefficient of resistance. Then these are some applications which are modeled as purely resistive loads: heater, incandescent bulb, iron box, etc. Okay, na? Our transmission lines also have a lot of resistance in ohms per phase per kilometer. Then I gave an example application. This cube-shaped material is stretched to double its original length. Then here what happened is length is doubled but area is halved. So total 4 times it is increased. Inductance represents electromagnetic property of matter. Okay, and it is classified based on the core material: iron core, ferrite core, silicon steel, etc. Units, range, Ohm's law for any signal. This is very important. We will start inductor capacitor in chapter 4, sir. Until then, wait. Okay. Then construction formula. Okay. What are the terms there? Then what are the applications which can be modeled as inductors? Transmission lines, current limiting reactors, electromagnets, AC machine, transformers. They're all modeled as inductors. Then I gave an example that a coil has a time constant of this. Of course, it is a practical coil with R and L, and R represents the resistance of winding. If the number of turns of the coil are doubled, of course, inductance become 4 times, but the resistance also becomes double as the length of the wire is doubled. So time constant only becomes 2 times. Then capacitance. Of course, capacitance represents electrostatic property of matter, classified based on the dielectric materials. Symbol, units, range. Okay. Ohm's law for any signal. Okay. Then basic formula, parallel plate capacitor. And then passive RC filters, phase shifting, pulse and digital circuits. This is where you will find capacitor applications. Then I gave an interesting example that this capacitor, parallel plate capacitor, is dipped in ethyl alcohol up to half the distance between the plates. Then this is like 2 series capacitors where charge density is uniform but working voltages are different. So series model, so C1, C2 by C1 plus C2. Then ideal voltage source, practical voltage source, of course DC basics first, and based on static VI characteristics we simplified. Then ideal current source, practical current source, and again based on static VI characteristics. Independent source, okay, properties are independent, they don't exist but we model them. And dependent sources, okay, they are represented by diamond symbol. There are 4 basic types. Dependent sources have internal sub-circuit resistance, we cannot neglect them. Then power function, okay, power function, of course, but average power and average power in a pure inductor and pure capacitor is 0 for any cycle of waveform, which I will prove. Then energy function, okay, yes, energy is integral power dt and energy in inductor capacitor. Then we demonstrated Kirchhoff's law. Kirchhoff first law is Kirchhoff current law. I give the notations how I write. I gave some examples. Then Kirchhoff second law is Kirchhoff voltage law. Again, I gave an example. Okay, so let us continue from here, everybody. Yes, let us continue from here. Okay, now. Okay, now, sir. So after understanding this Kirchhoff's laws, now let us continue further. Okay, now let us understand series and parallel connection of elements. Okay, now I'm going with a topic called series and parallel connection of elements. Okay, now series connection of elements. Okay, now you know what is the meaning of series connection, sir. So first of all, in series connection, suppose there are 2 elements. Okay, when can you say they are in series? Okay, when the output terminal of first element is connected to the input terminal of second element. Okay, so this is called series connection. When the output terminal of first element is connected to the input terminal of second element, it is called series connection. Of course, in series connections, yes, of course, in series connection, current through them is equal. Equal means equal in magnitude and equal in direction. Current through them equal means, of course, equal in magnitude and also equal in direction. Okay, current through them is equal means equal in magnitude and also equal in direction. Now these things you know, sir. Of course, you know resistors in series R1, R2. Then resultant is greater than the greatest, R1 plus R2. Okay, then inductors in series. Inductors in series, of course, I am neglecting mutual inductance. Okay, that is L1 plus L2. Okay, L1 plus L2. Then capacitors in series. Capacitors in series. Okay, here also resultant is lower than the least. So 1 by C series is 1 by C1 plus 1 by C2. That is C1 C2 by C1 plus C2. Okay na? Of course, if more elements are there, keep on adding like this. That is why I wrote like this. Okay. But for 2, you can understand the formula. But here in inductance, I am neglecting the mutual inductance. Okay. Here in inductance, I am neglecting the mutual inductance. Okay. Now that you have to understand. I am neglecting what mutual inductance. Okay. Then I am asking an interesting question. Everyone should answer this. Okay. Now here I am asking find voltage V. Now everyone should understand. Find voltage V. Okay. Now let us say this is some 3 amperes, 1 ohm, 2 amperes, 4 ohm. I need this voltage V. Chalo, how much is this voltage V? Anyone can guess? How much is this voltage V? Anyone can guess, please? Anyone can guess? How much is this voltage V? Yes, you cannot tell here. You can never connect. Everybody listen. So you can never connect two current sources of different values in series. That is violation of KCL. Why? Because suppose at this junction you see this is 3 amperes entering, but suddenly 2 amperes. Where 1 ampere went, sir? So this is violating KCL. See, this is violating KCL. So what is the rule? Never we can connect two current sources of different values in series. Okay, na? Never we can see some students are giving answers which is wrong, sir. No. Yes, some student wrote. Yes. See, never we can connect. Yes, never we can connect two current sources of different values in series. That is violating KCL. But if you still want to connect two current sources in series, make sure that their magnitudes and direction are same. If you still want to connect two current sources in series, make sure that their magnitudes and directions are same. But otherwise, we cannot connect two current sources in series. That is violation of KCL. Yes or no? We cannot connect two current sources in series. That is violation of KCL. Okay. Then what about voltage sources? Now this is also interesting. Now see, I am connecting now two voltage sources in series. Okay. Let us say this is some 10 volts. And let us say this is some 3 volts. Now I am asking this voltage V. This is not clearly how much 10 plus 3, 13. Na? Yes, 10 plus 3, 13. Now suppose I reverse this polarity. Listen now. Suppose I reverse this polarity. Like I put minus here, plus here. Then V is how much? Minus 7. Because you write a KVL, na sir. Minus 3 plus 10 plus V is 0. V is minus 7. Suppose I reverse this polarity also. Minus plus. Then V is how much? Then V is how much? V is minus 13. V is how much, sir? V is minus 13. Then finally, if I reverse this. Finally, if I reverse this. This is plus and this is minus. Now V is how much? V is plus 7 volts. V is how much? Plus 7 volts. So voltage sources of any values and any polarities can be connected in series. But two current sources of different values can never be connected in series. That is violation of KCL. But if you still insist to connect two current sources in series, make sure that they are equal in magnitude and equal in direction. Okay. If you still insist to connect two current sources in series, make sure that they are equal in magnitude and equal in direction. Okay. That is the meaning. So simple, sir. Resistors, inductors, capacitors, voltage sources, current sources. That is the simple meaning of series connection of elements. Okay. Na? Then I am now going to parallel connection of elements. Okay. Parallel connection of elements. Doubts only after the session. Note down. Parallel connection of elements. Parallel connection of elements. See, when can you say elements are parallel? Yes, when can you say elements are parallel? See, connection wise, we can say elements are parallel if the input terminals, yes, if the input terminals of both elements are connected together and correspondingly the output terminals are also connected together. Okay. Yes, if input terminals and output terminals are both connected together. See, the input of this and input of this are connected and the output of this and output of this are correspondingly connected. Okay. The corresponding input terminals connected together and the corresponding output terminals connected together, then it is called parallel connection of elements. In parallel connection of elements, voltage is same. Voltage across elements. Voltage across elements are equal. Equal means equal in magnitude and equal in polarity. Equal means equal in magnitude and also equal in polarity. Now, sir, we know this. Now, resistors in parallel. See, when resistors are in parallel, resultant is lower than the least. Like 1 by R parallel is 1 by R1 plus 1 by R2. So for two resistors, it is R1, R2 by R1 plus R2. But if more than two are there, you keep on adding 1 by R3, 1 by R4. Suppose 1 ohm is in parallel to 100 ohm, answer is less than 1 ohm. 1 ohm in parallel to 100 ohms, answer is less than 1 ohm. Then inductors in parallel. Here also I am neglecting mutual inductance. Inductance in parallel. Okay. So resultant is again lower than the least. 1 by L1 plus 1 by L2. Now capacitors in parallel. Capacitors in parallel. Okay. Capacitors in parallel. Okay. This is C1, this is C2. Here resultant is greater than the greatest. Okay. Here resultant is greater than the greatest. Okay. So remember that. This all because of Ohm's law we get. Then I am asking a question. Suppose there are two current sources in parallel. Okay, suppose there are two current sources in parallel connected to some element or load. Okay, element or load or network. Let us say this is now 10 amperes. And let us say this is now 3 amperes. Now I am asking what is this current I? So what is this current I? Apply KCL. 10 plus 3 they become 13. 10 plus 3 is 13. That means we can connect current sources in parallel, sir. That is not an issue. See, previously current sources in series is violation of KCL, but current sources in parallel is okay. Now suppose I reverse this direction. Carefully listen, I reverse this direction. Then what is I? See, this is 10, this is 3. So this has to be 7 in reverse direction. See, this is 10, this is 3. This has to be 7 in reverse direction. So I is minus 7. I is minus 7. Now suppose here also, I reverse the direction. Then this is 3, this is 10. So total 13 going this way. 13 going left side, it is opposite. So I is minus 13. I is minus 13. Then finally I reverse this. So finally I reverse this. Okay. Finally I reverse this. Okay. Out of 10, 3 went. Out of 10, 3 went. So this is how much? Plus 7. Out of 10, 3 went. So I is plus 7 amperes. I is plus 7 amperes. So current sources of different values can be in parallel. Okay. They obey KCL. Then what about this? Now suppose here interesting I am asking what is the value of current I? Everybody should answer this. What is the value of current I? Okay. Everybody again answer what is the value of current I? Everybody should answer the value of current. Here not possible, sir, because we are violating KVL. See, I told KVL can be written in a mesh loop or anywhere. Yesterday I told now, though we defined KVL as Kirchhoff's mesh law because mesh is a simplest and independent loop, but actually KVL valid in any path. Suppose I write KVL like this in the outermost loop. See, minus 10 plus 5, is it 0? No, minus 10 plus 5 is violating KVL. That means never we can connect two voltage sources of different values in parallel. So ideal voltage sources of different values in parallel is violation of KVL. But if they were practical sources with internal resistance, then I can connect, sir. I know practically we connect alternators in parallel, batteries in parallel. But if they were having some internal resistance, but these are ideal sources. Circle symbol means ideal independent sources. Never we can connect to ideal voltage sources in parallel. That is violation of KVL. Please understand. Never we can connect to ideal voltage sources in parallel. That is a violation of KVL. So I cannot be determined. Okay. But if you still insist to connect, okay, but if you still insist to connect two voltage sources in parallel, make sure that they are equal in magnitude and equal in polarity. In DC we can say, if you still insist to connect two voltage sources in parallel, make sure that their magnitudes and polarity are same. Okay, na? Magnitudes and polarity are same. Then definition of open circuit. Okay, now definition of open circuit OC. Okay, definition of open circuit OC. In an open circuit, okay, everybody, in an open circuit, current is zero for any voltage. For any voltage, in an open circuit, current is zero for any voltage. So resistance of open circuit is any voltage by zero, which is infinity ohms. Okay, in an open circuit, current is zero for any voltage. So resistance of open circuit is zero voltage by, yeah, any voltage by zero current, that is infinity ohms. That is infinity ohms. Any passive element, yes, any passive element, okay, in series to open circuit can be neglected. First passive elements only I am arguing. Later what happens to independent dependent source, that I will talk later. Okay, then what happens to, see, in our subject the passive and active elements are there. Again, in active elements, independent and dependent sources are there. So that I will talk later. Such things only when we come to Thevenin's we can understand. So in an open circuit, yes, in an open circuit, current is zero for any voltage. Okay, in an open circuit, current is zero for any voltage. Okay, now please understand, current is zero for any voltage. Resistance of open circuit is infinity. Any passive element in series to open circuit can be neglected. Suppose I give an example here. Passive elements only first time talking. Suppose I write like this. Okay, a simple network like 10 volts, 1 ohm, 2 ohm, 3 ohm, 4 ohm. So what is my argument? Now this is open circuit. Okay, now this is open circuit. So any passive element in series to open circuit is neglected. It won't work now. So it is not a working branch. Okay, so we can neglect it. Then short circuit SC. Short circuit. Okay, short circuit. Now in a short circuit, okay, now let us understand. In a short circuit, voltage across shorted terminals, please understand, voltage across shorted terminals is zero for any current. For any current. That remaining current depends upon the remaining path impedance, etc. So in a short circuit, voltage across shorted terminals is zero for any current. So resistance of short circuit. Okay. Now resistance of short circuit is any voltage by, okay, zero voltage by any current. Okay, zero, because R is V by I. Zero voltage by any current. So 0 ohms. So it is 0 ohms. Okay, so it is 0 ohms. Okay, so now I write any passive element completely in parallel to short circuit, can be neglected. Okay, any passive element completely in parallel. Now please don't misunderstand. In a short circuit, voltage across shorted terminals is zero for any current. Please understand, voltage across shorted terminals is zero for any current. That does not mean that voltage is zero, current is flowing. No, voltage across short terminals is zero for any dangerous current bypassing it. That remaining current depends upon what? That remaining current depends upon the remaining path resistance. Okay. Then any passive element completely in parallel to short circuit is neglected. Like for example, here also first only passive element I am teaching, sir. Because independent dependent sources we will study later. Okay. There after Thevenin's I will teach them. Now suppose I take an example like this. Okay, I am taking an example like this. Like some 10 volts, 1 ohm, 2 ohm, 3 ohm, 4 ohm, 5 ohm, and I am creating a short circuit across 4. Now see, any passive element completely in parallel to short circuit. This is short circuit now. Yes, this is short circuit. Any passive element completely in parallel to short circuit is neglected. So it is bypassing 4 and going through 5. But this current is flowing because of the remaining voltage and remaining path resistance. Don't forget that. But don't misunderstand, sir. Potential difference across short is zero. How current is flowing? No. In order to make these two potentials equal, current has to flow. Okay, in order to make these two potentials equal, current has to flow. That is the meaning. So in a short circuit, potential difference across shorter terminals is zero for any current. That remaining current depends upon the remaining path resistance. Okay, and what we can say in a short circuit, potential difference across shorter terminals is zero for any current. Okay, potential difference across shorter terminals is zero for any current. Okay, na? That is how you have to argue. Okay, potential difference across shorter terminals is zero for any current. Okay, na? That is the meaning there. Now I ask this question. I always ask this question: which is dangerous? Which is? See some students. Haripriya, please down your hand. Gautam and Harika, please down your hand. See, any good doubt, I respect it, but ask after 10:30. Let it be any silly doubt, sir, no problem. Remember the slide, remember the topic, ask. And this Harika, you are still not putting your down. Okay, I may suspend you, please. Because, sir, while writing, these things disturb us, sir. Please understand. Problem is that here, see, now there are so many students in my class. Individual doubts, if I take not even a single class, I can complete. But after 10:30, ask. Okay, na? And I told na sir, once I complete to conclusion of subject, I will give my WhatsApp number also. You can ask anything. You can take any Photoshop and tell me, sir, this question I'm having doubt, which I will do it. Okay, I will share you my notes also. Everyone, I will really share you my notes also. Okay, don't worry. But still, this class is very important. What I'm writing is detailed actually, better than my notes. Because while explaining and teaching NASA, the quality is different. Though there is a soft copy of my notes, but this notes, what I'm writing is more important. So please listen carefully, okay? Okay, now see here. I ask this question. Which is more dangerous and why? Open circuit or short circuit? Okay, which is more dangerous and why? Okay, which is more dangerous and why? So Arika, put down your hand. Arika, put down your hand. Okay, which is more dangerous and why? Open circuit or short circuit? Okay, please understand. Which is more dangerous and why? Open circuit or short circuit? See, everyone say, array, short circuit is dangerous. No, sir. Short circuits actually will allow more dangerous current to flow through the equipment. But instead, if you have fuses and circuit breakers, you can always protect them. Please understand this. Short circuits are easy to protect. Okay, everybody, understand this. Short circuits are always easy to protect because any dangerous short circuit current can always be protected by using proper fuses and circuit breakers. But open circuits in high voltage engineering are not so easy to protect because of insulation problem. We always say, sir, short circuit is dangerous. No, sir. Short circuits will create fire, but short circuits will not create direct loss of life. But because of excess short circuit, fire may come, wire may burn, equipment may burn, and fire may indirectly kill us. But if you design proper equipment like current limiting reactors, fuses, circuit breakers, fire alarms, etc., short circuits are always easy to protect. But open circuits in high voltage, there is no protection because of insulation level. That is why, sir, please understand, electrical people, in fact, according to me, open circuit in high voltage engineering are deadly dangerous than short circuits. Okay, so I'm writing here, I'm writing which is more dangerous and why. My answer is open circuits. Yes, open circuits. Okay, live wire faults, live wire, I will write. Okay, open circuit charge is called live wire. Open circuit live wire faults. Okay, faults in high voltage engineering. In high voltage. Okay, in high voltage engineering. Okay, in high voltage engineering. Okay, are more dangerous. Are more dangerous. Okay, than short circuits. Okay, please understand. Open circuit live wire faults in high voltage engineering are more dangerous than short circuits due to insulation material limitations. Insulation material limitations. Okay, so there is no insulation for every level, sir. Always understand. However, short circuits can always be protected, okay na? Always be protected both at LV level and HV level. Short circuits can always be protected both at LV level and HV level, okay, by using proper uses circuit breakers, okay, current limiting reactors, fire alarms, etc. See, this is my simple statement. Okay, please understand which is more dangerous and why. Okay, according to me, open circuit live wire faults in high voltage engineering are more dangerous than short circuits because insulation is problem. In fact, short circuits can always be protected by using fuses and circuit breakers, current limiting reactors, fire alarms, etc. Okay, if you don't have such protection, then short circuit fire will come and because of fire you may die. But short circuits will not kill us directly. In fact, open circuit live wire faults are more dangerous than short circuits. Okay, now I'm just asking this question. What is RAB? That is resistance between A and B. Okay, what is RAB? Okay, simple concept. What is RAB? I am asking here. 1 ohm, 2 ohm, 3 ohm, 4 ohm, 5 ohm, 6 ohm. This is A and this is B. Shall I write some answer? What is RAB? Just write some answer. What is RAB? So, if someone asks which is dangerous, actually, we are always fond of short circuits, now, sir. We feel that is dangerous. Actually, short circuits are protectable. Always remember that. But open circuits, yes, sir. High voltage engineering, open circuits are more tough to protect. Always remember that. Okay. High voltage engineering, open circuits are more tough to protect. Here I'm asking what is RAB. So my simple explanation is, see everybody, yes, answer is 8 ohms. Yes, resistance is offered by that path where current can flow. Okay, I want to teach like this initially, sir. I know I gave open circuit and short circuit, but see here, resistance is offered by that path where current can flow. Okay, resistance will not stop current, sir. Resistance will control the magnitude of current. Please understand. Resistance will not stop the current. Resistance will always control the magnitude of current. Okay, na? Resistance will never stop current, but resistance will control the magnitude of current. Okay. So suppose I give voltage here. Okay. Now based on the network resistance, current will flow. I is V by R. But whatever current you has to come back now. Yes, whatever current you has to come back. That is law of conservation of charge. So whatever current leaving has to come back. Now let us see which path current can flow. So current requires two things: driving force, voltage, and closed path. Current requires voltage and closed path. Voltage I gave. Now let us see the closed path. Current will go here, go here, go here. Now can it go through two? No, no, sir. Yes, open circuit in series to passive element is waste. It cannot go. Again, can it go through 5 and 6? No. because short circuit, yes, short circuit in parallel to passive elements are also waste. So current will bypass this element because there is no potential difference to go there, and it will come back here only. So this dotted path is the path which contribute resistance. So resistance is offered by that path where current can flow. Open circuit in series to passive elements won't work. Short circuit in parallel to passive elements also won't work. So this dotted path is only path where current is flowing. So 1 plus 4 plus 3. So RAB will be 1 ohm plus this is 4 ohm plus 3 ohm. 4 ohm plus 3 ohm. Total 8 ohms. Total 8 ohms. Okay, that is total 8 ohms. Okay, now like that example. So now I'm talking about conductance. Conductance. Okay, it is another passive property. It is the ability. It is the ability. Okay, ability to conduct. Ability to conduct electrically. It is the ability to conduct electrically. It is used. Okay, it is used to further classify. Okay, it is used to further classify metals because metals are excellent conductors. Okay, actually resistance is there to classify. Okay, now we already know resistance is there to classify, but why we are learning to further classify in detailed and precisely metals, because all metals are very good conductors. So they started giving conductivity. So conductance is the ability to conduct. It is used to further classify metals. But conductance is reciprocal of resistance. Conductance is reciprocal of resistance. Okay, its units are mho, ulta. Okay, mho or Siemens. Its units are mho or Siemens. Siemens. Okay, its units are mho or Siemens. Okay, now conductance representation. Yes, it is simple like resistance. Okay, and it is passive property. The direction in which current enter is taken as positive. Okay, it's passive notation only. Okay, ideal conductance, infinite conductivity. Practical, less limited conductivity. Okay, that is the meaning. Ideal conductance, infinite conductivity. Practical conductance, limited conductivity. Okay, now Ohm's law. We already know, yes, Ohm's law, because it is inverse relation to resistance. Here V equal to I by G. V equal to I by G. Or I equal to V into G. I equal to V into G. Okay. Then basic formula. Yes, here also basic formula. Okay. There in resistor we wrote R equal to rho L by A. Here A by rho L. Okay, but 1 by rho is what? Sigma. Sigma A by L. Because 1 by rho is called sigma. So conductance or conductivity, yes. Where sigma is called conductivity. Conductivity. And its units are ohm meter inverse. Ohm meter inverse. That is mho per meter or Siemens per meter. Siemens per meter. Okay, na? So yes, conductance is the ability to conduct. R is rho L by A. This is A by rho L. But 1 by rho is sigma. 1 by rho is sigma. Sigma A by L. But sigma is called conductivity. Okay. Now units of conductivity is ohm meter inverse or mho per meter or Siemens per meter. Okay, na? Siemens per meter. Okay, na? Okay. Then conductances in series. See here, conductances in series ulta to resistance. Resultant is lower than the least. 1 by G series is 1 by G1 plus 1 by G2. If more are there, keep adding like this. Then conductances in parallel. Conductances in parallel here, resultant is greater than the greatest. Conductances in parallel is resultant is greater than the greatest. Okay, again power absorbed by conductance. It is either voltage into conductance into current through conductance. Okay, or it is I square by G, or it is V square into G. I am putting suffix for voltage and current to stress that it is the elemental voltage and current I am talking. Okay, no, not supply. It is the element. So there in register I square R come. Here it is I square by G. Okay, and there V square by R, here V square into G. Okay, watts. Units are of course watts. Okay, units are of course watts. Now, I would like to conclude that based on conductivity, yes, based on conductivity, rank one material is, yes, silver. Silver is the best conductor in the world. Okay, based on conductivity, yes, silver is the best conductor in the world. Okay, then rank 2 is copper. Rank 2 is copper. Then rank 3, yes, rank 3 is gold. Then rank 4, yes, rank 4 is aluminium. Aluminium. Okay. Yes. Rank 1 is silver, rank 2 copper, rank 3 gold, and rank 4 aluminium. Then I would say now silver and gold are highly uneconomical, costly. But copper is best used, yes, best used in high current density. High current density, and compact wiring, where domestic, yes or no, domestic machines, okay, machines, industrial wiring, etc. Industrial wiring, etc. We use copper. Then where we use aluminium, aluminium has two advantages. One, it is lightweight, and also cheap, and also very cheap. Okay, they are used in, yes, used in external T&D lines, external transmission and distribution lines. Okay, aluminium core, steel reinforced, we say. Yes or no? That is aluminium core, steel reinforced, we say. So there is a simple observation, sir. So based on conductivity, this classification is coming. Rank 1 is silver, rank 2 is copper, rank 3 is gold, and rank 4 is aluminum. But silver and copper, silver and gold are highly uneconomical, sir, costly. Then copper, but where copper is used, high current density compact system, and aluminum, yes, lightweight and cheap. They are used in external T&D lines. Okay, where they are used, sir? They are used in external T&D lines. Okay, na? Now I'm coming to voltage division rule. Voltage division rule. Okay. Voltage division rule is applicable in series connected elements only. In series connected elements only. Okay, in series connected elements only. Okay, first I will take resistors. Suppose I take two resistors in series. Okay, and I am giving total voltage V. This is R1, this is R2. Okay, now I want to write V1 and V2. Okay, now this V1 is total voltage into, okay, same by sum, same R1 by sum, R1 plus R2. Okay, then total volt, this V2 also is total voltage into same R2 by R1 plus R2. This all comes from Ohm's law, sir. They are not even like derivations, you can derive it. See, actually I'm giving total voltage V across two series connected resistors. Okay, I'm giving total voltage V across two series connected resistors. Yes or no? Yes, I am giving total voltage V across two series connected resistors. Okay, yes, across two series connected resistors. Then what is V1? V1 is the voltage across R1, which is total voltage into R1 by R1 plus R2. Here V2 also, let me correct it, sir. And V2 will be total voltage into R2 by R1 plus R2. Okay, na? This is R2 by R. That means voltage division is proportional to resistance. Simple. Okay, na? Then similarly for inductors, what happened? Suppose two inductors are series. VL1 will be total voltage into L1 plus L1 by L1 plus L2. VL2 is also equal to total voltage into L2 by L1 plus L2. Okay. Now, but if they are capacitors, yes, if they are capacitors, ulta, sir. Because in capacitor, V is 1 by C integral IDT. Yes or no? V is 1 by C integral IDT. Voltage division is inversely proportional to capacitance. So VC1 will be total voltage into C2 by C1 plus C2. And VC2 will be total voltage into C1 by C1 plus C2. Okay. So there VC1 is total voltage into C2 by C1 plus C2, and VC2 will be total voltage into C1 by C1 plus C2. Okay. Similarly for conductance. Now we learned even conductance, now that also I am adding. VG1, where G is the conductance, total voltage into, it is ulta to resistance, na, sir? G2 by G1 plus G2, and VG2 will be total voltage into G1 by G1 plus G2. Of course, resistance in ohms, inductance in Henry, capacitance in farads, and conductance in Siemens. Okay, na? That is the meaning, conductance in Siemens. Okay, that you remember, conductance in Siemens. Okay, na? Then, yes, then I will extend for more elements in series. Suppose these are all formulas for 2 elements in series, but suppose there are n resistors in series. Okay, like there are n resistors in series. Okay, and I'm giving total voltage V across this series string. I'm giving total voltage V across this series string where this is R1, R2, R3, so on to Rn. And I want this voltage V3 alone. I want suppose this voltage V3 alone. Then this voltage V3 is total voltage into R3 by sum of all resistance R1, R2, R3, so on to Rn. Okay, that I will write it as total voltage into R3 by sigma Ri. I take in the value from 1 to n like that. But suppose these are capacitors. Suppose they are capacitors. They are capacitors. Okay, now suppose they are capacitors. Inductor also same formula like resistors are, like VL3 will be total voltage into L3 by sum of all inductors. But suppose they are capacitors, then reciprocate. Suppose this VC3, suppose imagine these are C1, C2, C3, so on to Cn capacitors. Then VC3 will be total voltage into reciprocate 1 by C3 by, okay, this is 1 by C3 by sigma 1 by Ci. Again, I is taking the value from 1 to n. Okay, so this total voltage into 1 by C3 by sigma 1 by Ci. Again, I taking the value from 1 to n. Okay, again, I taking the value from 1 to n. Okay, that is the meaning there. Okay, like 1 by C1, 1 by C2, so on to 1 by C, like that. Okay, now remember such things you remember. Okay, now then I want to write a note. That the formulas for resistance, okay, inductance, reactance, and impedance is like one set. It is like one set. Okay, these are all proportional. Okay, because V equal to IR, V equal to LdI by dt, reactance V equal to plus JX into I, and impedance V is Z into I. See, this reactance impedance will come in AC steady state, sir. But now only remember these relations. Then the formulas for conductance in Siemens, capacitance in farads, susceptance in Siemens, and admittance in Siemens. This is like another set, ulta set, reciprocal set. Why? Because here in conductance V is I by G, capacitor also V is 1 by C integral I dt. Here V is 1 by JB. Here V is I by Y. So the formulas for resistor, inductor, reactance, impedance is like one set, and formulas for conductance, capacitance, susceptance, and admittance is one set. Like here you see in voltage division rule, see formulas for resistor and inductor is like similar, because here voltage drop is proportional to resistance, proportional to inductance. Similarly, it will be proportional to reactance and proportional to impedance. But you see the formulas for capacitance and conductance is ulta na, inversely proportional. So similarly, the formulas for conductance, capacitance, susceptance, admittance are ulta. Okay, now I am talking about current division rule. Current division rule. Okay, now when can you say current division can be applied? Yes, current division can be applied. Yes, applicable only if elements are parallel in nature. Only if elements are parallel connected only. Parallel connected only. Okay. Yes, current division rule is applicable only if elements are parallel. Now suppose first let us talk about resistor. Let us imagine there are two resistors in parallel. And I am driving with a constant current I. This is R1, this is R2. Now I want this IR1 and IR2. Okay. Then current division is inversely proportional. Yes, please understand. Current division is inversely proportional to resistance. So this current I1 is total current into opposite R2 by some R1 plus R2. And this current I2 is again total current into opposite R1 by R1 plus R2. Like, okay, na? Like, okay. So please understand. Similarly, inductor also, sir, because in inductor I is 1 by L integral VDT inversely proportional. IL1 will be total current into L2 by L1 plus L2. IL2 will be total current into L1 by L1 plus L2. Okay, but what about capacitors? Nah, capacitor I is CdV by dt. I is CdV by dt proportional to capacitance. IC1 will be total current into C1 by C1 plus C2. Okay, yes, C1 by C1 plus C2. And IC2 is total current into C2 by C1 plus C2. Okay, then conductance also proportional to conductivity. Ig1 will be total current into G1 by G1 plus G2, and Ig2 is total current into G2 by G1 plus G2. Okay, G1 plus G2. Okay, that is the meaning. That is a wonderful meaning here. Okay, so here also suppose there are three. Now I am taking three resistors in parallel. Okay, I am giving another formula. This is very important. Three resistors in parallel. For two resistors, everyone knows, sir. Okay, suppose there are three resistors like R1, R2, and R3 are in parallel, and I am giving total current I. Now I want only this. Let us say IR2. Okay, I want only IR2. So what is this IR2? IR2 will be total current into first product of remaining two. What is product of remaining two? R1, R3 by sum of products like R1, R2, okay, plus R2, R3 plus R3, R1. Okay, na? So this IR2 will be total current into product of remaining two R1, R3 by sum of products. But suppose if it is IR3, IR3 will be total current into product of remaining two R1, R2 by sum of products. Now I write suppose these are capacitors. Suppose I use capacitors. Inductors, I told na sir, resistor, inductor, impedance, reactance is same form. But suppose these are capacitors. In capacitors, yes, suppose these are C1, C2, C3, T3 capacitors. C1, C2, C3 are three capacitors, and I'm giving total current I. Now I want current in capacitor C2 alone. IC2 will be total current into product of remaining two, but reciprocate like 1 by C1 into 1 by C3 by sum of products, but reciprocate 1 by C1, 1 by C2 plus 1 by C2, 1 by C3 plus 1 by C3, 1 by C1. Please understand what I am trying to say. Okay, this IC2 will be total current into first product of remaining two, but reciprocate 1 by C1, 1 by C3 by sum of products, but reciprocate. Okay, sum of products, but reciprocate. 1 by C1, 1 by C2, 1 by C2, 1 by C3, and 1 by C3, 1 by C. Okay, now there is a difference. Okay, so now suppose there are four resistors in parallel. In IES, this bit was asked, sir. Suppose four resistors in parallel. Only to waste your time, sir. Not that it is tough, sir. Suppose there are four resistors in parallel. Okay, and I'm giving total current I, R1, R2, R3, R4. Now I want current in R4, IR4 only suppose. Okay. Yes, then what to do? Yes, this IR4 will be total current into first product of remaining three. R1, R2, R3 by sum of products. R1, R2, R3 plus R2, R3, R4 plus R3, R4, R1 plus R4, R1, R2. Okay, R1, R2, R3. Now R1, R2, R3, R2, R3, R4, R3, R4, R1, and R4, R1, R2. Like that. Okay. Similarly for capacitors, you can write. But here also I will write a note. The set of formulas for resistance in ohms, inductance in Henry, reactance in ohms, and impedance in ohms is one set of formula where all are proportional. But conductance in Siemens, capacitance in farads, susceptance in Siemens, impedance in Siemens is second set of formula. This is second set of. Okay, remember that. Okay, these are very, very important things, sir. Now, after understanding that, yes, I am going to star to delta, delta to star transformations. First, I will go to delta to star transformation, delta to star. Suppose imagine there are three registers in delta. Suppose imagine there are three registers in delta. So this is node 1, node 2, node 3. Let us say this is RA, RB, R3. It is connected to the rest of the network. Okay, suppose there are three registers in delta. Now I'm converting them into star. Okay, this green color part is a conversion where this is R1, where this is R2, and where this is R3. So now what is this R1, R2, R3 in terms of RA, RB, RC? This R1 will be first product of these two. See, R1 is here now. Don't try to by heart formula. How to implement, you see. This R1 is here now. Product of the other two adjacent. So that is RA. Let me take this as RC, sir. Please correct it. I'm repeating. First we are learning delta to star transformation. What is the meaning of delta to star? So I'm converting delta connected equivalent network to its star equivalent. So between three nodes, there are three registers in delta connection form like RA, RB, RC. Now I want to convert them into star connection like R1, R2, R3. So this is a star point. So I want to convert the delta white color network into star green color network. Then what is R1? R1 is this into this. Adjacent to you take. Adjacent to is what? RA, RC, RA, RC by sum. Sum is RA plus RB plus RC. Then where is R2? Chalo, R2. Where is R2? Again, product of this by sum. Product. What is product? RA, RB by sum. RA plus RB plus RC. Where is R3? Where is R3? Okay, R3 where it is here? Again, product of these two. That is RB, RC by sum. That is RA plus RB plus RC. Okay, na? Yes, like that. So just product of remaining two by sum, like that. Okay, you see, like R3 is here now. This into this, like RB, RC by sum. Now here also inductors same are in inductors also like LA, LB, LC are in delta. I want corresponding star. So L1 will be LA, LC by sum LA plus LB plus LC. Similarly L2, L3 you write it, sir. Don't worry. Okay. But if these are capacitors, if these are capacitors, same like resistor but reciprocate including the left hand side. Same formula like resistors, but reciprocate every term including the left hand side. Like suppose CA, CB, CC are three capacitors in delta. CA, CB, CC are three capacitors in delta. I want the corresponding star equivalent like C1, C2, C3. Then this 1 by C1 is, okay na, this 1 by C1 is this into this, like 1 by CA into 1 by C by sum. 1 by CA plus 1 by CB plus 1 by CC. Like that you can complete the remaining two. Okay. So don't try to simplify, sir. Leave it. Because if you can remember, see, my intention is if you can remember the register formula, remaining are easy. Okay. But capacitor also same like register formula, but reciprocate every term including the left hand side. 1 by C1 is, okay, 1 by CA into 1 by CC by sum, but reciprocate. Similarly, conductance also. Suppose imagine three conductance GA, GB, GC are in delta. I want its equivalent star. 1 by G1 is, yes, 1 by GA into 1 by GC by sum. 1 by GA plus 1 by GB plus 1 by GC. Remaining you can write. Okay, remaining you can write. Okay, remaining you can write. Okay, so the set of formulas for resistance, inductance, reactance, impedance is similar. Conductance, capacitance, admittance, and susceptance are ulta. Okay, now remember like that. Okay. Then further extending. Now I am converting. Yes, star to delta. Star to delta. Okay. Yes, let us say there are three registers in star between three nodes. Let us say there are three registers in star between three nodes. Okay. This is node 1, R1. This is node 2, R2. This is node 3, R3. I want to convert them into delta. I want to convert them into delta. I want to convert them into delta. Okay, let us say this is RA, this is RB, This is RC. Okay, this is RA, RB, RC. Okay, I want to convert this into, yes, I want to convert this into star to delta. Okay, na star to delta. Okay, chalo. Now first, where is RA? Okay, yes, RA is here. This RA will be this plus this, that is R1 plus R2 plus product R1 R2 by opposite. Opposite, what is opposite? R3. What is the way? Similarly, where is RB? Chalo, RB is here. Where is RB? RB is here. First sum of these two, that is R2 plus R3 plus product R2 R3 by opposite to that. What is opposite to that? R1. Finally RC. Where is RC? Yes, sum of this. R3 plus R1 plus R3 R1 by opposite. What is opposite to this? R2 R3. Now here also, if they are all inductors, I want to convert them from star to delta. So this LA will be L1 plus L2 plus L1 L2 by opposite L3. Okay, by opposite L3. Similarly, LB and LC also you can do. Okay, then capacitors. Suppose capacitors. There are 3 capacitors in star, the corresponding value in delta. Okay, so this 1 by CA is equal to 1 by C1 plus 1 by C2 plus 1 by C1 into 1 by C2 by opposite 1 by C. Okay. Okay, that's the meaning. So 1 by CA is 1 by C1 plus 1 by C2 plus 1 by C1, 1 by C2 by opposite. Okay, that is how you can go. Okay. Reciprocate every term including the left hand side. That is what you have to remember. Similarly for conductance, yes. If there are 3 conductances in star, I want corresponding value in delta. This 1 by GA is, okay, that is 1 by G1 plus 1 by G2 plus product, but reciprocate 1 by G1 into 1 by G2 by opposite 1 by G3. So you can write the remaining things. Of course, here resistance in ohms, inductance in Henry, capacitance in farads, and conductance in Siemens. Okay, conductance in Siemens. Okay, we will use them, sir, wherever necessary. We are going to pakka use them. Okay, wherever necessary, we will use them. At the same time, suppose there are 3 equal resistors in delta. Suppose there are 3 equal resistors in delta, then the corresponding value in star become by 3, na, sir. Suppose R in delta, then this become R square by 3 or R by 3. So if there are 3 equal resistors in delta, the corresponding value in star become by 3. Similarly, if there are 3 equal capacitors in delta, the corresponding value in star become 3C. Ulta. Okay. Similarly, star to delta. Suppose there are 3 equal resistors in star. Suppose there are 3 equal resistors in star, the corresponding value in delta become 3R. Yes or no? Suppose there are 3 equal resistors in star, the corresponding value in delta become 3R. Similarly, there are 3 equal capacitors in star, the corresponding value in delta becomes 3 by 3. Okay, remember such things are simple observations. Okay. So now, sir, what are ratings or specifications? Ratings or specifications. Okay, na, important. Ratings or specifications. Okay, and they represent what they represent. Knowledge and ratings or specifications. They represent the maximum permissible, the maximum permissible or allowable, permissible or allowable. Okay, they represent the maximum permissible safe values for continuous operation. Okay, continuous operation of an electrical device. Yes, of an electrical device or application. Please understand that. Okay, please understand. See, though my subject is simple linear subject, but ratings are important. So as long as you design and operate them within the ratings, they are said to be linear. Okay, what are ratings? They represent the maximum permissible safe values. Okay, they represent the maximum permissible safe values for continuous operation of an electrical device or application. Okay, na? They represent the maximum permissible safe values for continuous operation of an electrical device or application. Okay, na? Maximum permissible safe values for continuous operation of an electrical device or application. Okay, that is the meaning of, yes, ratings or specifications. Okay, now we generally consider. Okay, we generally consider voltage, current, frequency. Okay, power. Okay, power, insulation class, and also temperature limitations, limits. So in electrical equipment, when you buy NASA, you should see all these things. What are the things you should see? Voltage rating, current rating, frequency rating, power rating, insulation class rating with insulation. Okay, now and temperature. Okay. Now operating any device or application, operating any device or application, okay, above the rated values, okay, leads to what happens, sir? Leads to damage, leads to deterioration or damage. Okay, deterioration means wear and tear, and damage permanently, and damage. So operating any device, yes, operating any device or application above the rated values leads to deterioration and damage. Yes, at the same time, operating any device or application, below the rated values, okay, below the rated values leads to, okay, below the rated values leads to underutilization or degeneracy, underutilization, or I call it as degeneracy. I will tell you, sir. Shall everyone read these 4 points I'm going to explain now? Read these 4 points I'm going to explain now, everybody. Read these 4 points I'm going to explain now. Okay, everybody. So what is the meaning of ratings? Sir, ratings are maximum permissible safe values for continuous operation, sir. Maximum allowable safe values for continuous operation. Suppose, sir, I can lift 100 kgs for 2 seconds. See, even though I can lift 100 kgs for 2 seconds, then 100 is not my rating. But I can lift 15 kgs continuously without any problem. Suppose if I can lift 15 kgs throughout the day, throughout the week, continuously without problem, then 15 is my rating. Even 16 kgs, if I lift, I may get back pain after 3 hours. But 15 kgs, I am not getting. So 15 is my limit. So ratings are the maximum permissible safe values for continuous operation. Okay. Intermittent, I can lift 100 kgs for 2 seconds, but 100 kgs is not a rating. Continuous ratings we call. But in subjects like power electronics, pulse and digital circuits, we may even take intermittent rating like pulsed power rating. So in some subjects like power electronics, surge current rating, impulse rating, fault current ratings, that are different, sir. But in my subject, generally steady state ratings are important. Steady state ratings means continuous steady state value. So ratings represents maximum permissible safe values for continuous operation of an electrical device. Then we generally consider voltage, current, frequency, power, insulation, class, and temperature. Now, operating any device or application above the rated values. Okay, operating any device or application above the rated values leads to deterioration and damage, but operating anything below the rated values leads to underutilization or degeneracy. Okay, that means above you go damage, sir, but below you go it will work, but it will not perform better. So both are important. Above the rating, damage, sir. Below the rating, underutilized. It won't give the best efficiency and performance. Okay, both are not good. So best operating point is generally ratings only. Okay, always remember. Best operating point is generally what? Ratings only. Okay, now. So now I will take an example. Suppose there is a practical wire. Okay, now listen carefully. Practical wire. Now in our domestic wire, yes, you know domestic wire, it is having insulation and copper strand. Okay, so let us take. I am taking wire in domestic wire, normal domestic wire, which is having insulation. Okay, and yes, inside there is copper wire. Okay, inside there is copper wire. Okay, this is copper wire. Inside there is a copper wire. Okay. Now, first of all, why this copper is stranded? Why this copper is stranded conductor? Stranded. Okay, stranded because one, to improve the mechanical flexibility. Mechanical flexibility will increase. Flexibility. See, pure copper is very brittle, sir. It will break once you bend. Pure copper is very brittle. But by doing stranded, okay, in Telugu we call Tegalu, stranded, okay, mechanical flexibility will come. And also to reduce skin effect. Yes, reduce skin effect. Now the skin effect you will learn in machines and power systems, sir. I don't want to explain. Even I know the reason, but you learn skin effect you will be taught in machines and power systems. So two things. First of all, copper is stranded. First of all, copper is stranded to increase the mechanical flexibility and to reduce the skin effect. Okay, now suppose I want to modify. Suppose let us say the ratings of this are 230 volts and 5 amperes. Okay, 230 volts and 5 amperes. Now I want to modify this. I want to modify this to 1000 volts wire and 20 amperes wire. Let us say, I want to modify this wire to 1000 volts and 20 amperes. What should be the change in design? What should be the change in design? Please understand my question. What should be the change in design to increase the voltage rating and current rating? Okay, now my question is, what should be the change in design to increase the voltage rating and current rating? Okay, what should be the change in design? Okay, now see, sir, listen to this. Okay, see, first of all, to increase the voltage rating, see, to increase current rating, first I will write like to increase current rating, conductor cross-sectional area must increase. Conductor cross-sectional area must increase. Conductor cross-sectional area must increase. Okay, to increase the current rating, conductor cross-sectional area must increase. Please understand. To increase the current rating, conductor cross-sectional area must increase. Okay, to increase the current rating, the conductor cross-sectional area must increase. And to increase the voltage withstanding capacity. To increase the voltage withstanding capacity. Okay, to increase the voltage withstanding capacity. Okay, insulation level must increase. Insulation level must increase. Okay, insulation level must increase. Please understand. So to improve the current rating of an equipment, the conductor cross-section area must increase. And to improve the voltage level, insulation level must increase. Okay, so that means this conductor becomes something like this. Very thick insulation, okay, or very special material so that it can withstand high voltage up to 1000 volts plus this conductor cross section area has to increase now, sir. So more copper strands will come. Now more copper strands. Okay, here more copper strands. Okay, more copper strands. So this area will increase, more current it can take, and this thickness will increase, more voltage it can withstand. So simple meaning. So if I want to simply increase the rating of any system electrically, what you have to think, if you want to allow more current through that equipment, conductor cross section area must increase. If you want to block more voltage, insulation level must increase. Okay, no, insulation level must increase. That is simple meaning there. Okay, that is a simple meaning. Okay, so conductor cross section area will increase the current rating, and so same applicable to another example. See another example, very interesting, sir. Everyone listen. Signal diode versus power diode. Okay, signal diode versus power diode. Where we use signal diode? Yes, in analog. We use signal diode in analog. Okay, now we use signal diode in analog, etc. Okay, power diode in power electronics, of course. We use signal diode in analog, and we use power diode in power electronics. Yes or no? Signal diode is analog and power diode in power electronics. Yes or no? Yes, power diode in power electronics. Chalo, now in that regard, everybody. Okay. Now suppose here the diode technical name is 1N4007. Okay. Its ratings are up to 60 volts. Okay. Some 880 milliamperes only. You know, this is a very small diode. Now you know that diode looks very, very small, sir. It is a very small PN junction. You studied in EDC analog lab, sir, electronic level. So it is a normal PN junction diode. Okay. PN junctions. Okay. It is a small diode where it can withstand up to 60 volts and only 80 milliamperes it can take. Okay. But power diode, some technical name like, okay, D104 by Philips Semiconductor. Let us say Philips. So it is designed for 1000 volts, 40 amperes. Now what is the difference then? Same concept. If you want to increase the current rating, cross section area, here the conductor means semiconductor only. The cross section area must increase. That is why, yes, this power diode cross section area will be very, very large. This power diode's cross section area will be very, very large. That is the first thing. Okay. And if you want to withstand more voltage, insulation level. So that is why here metal terminal 1, this is metal terminal 1, this is metal terminal 2. Of course, we call it as anode and cathode. Anode and cathode. So what happened first? I increase the cross-sectional area of the semiconductor material. So because I increase the cross-sectional area, now it can carry how much current? 40 amperes. Previously, the signal diode is hardly carrying 18 milliamperes. Then how to withstand high voltage? Insulation levels are insulation level. Now see here. In this, what happens now? Apart from P plus, and also N plus. See, apart from P plus and N plus material, okay, apart from P plus and N plus, there is a drift layer called N minus. Okay, so there is a drift layer called N minus. Okay, this is called drift layer. Okay, yes, please understand. Apart from P plus and N plus, okay, apart from P plus and N plus, there is an extra drift layer N minus. Okay, now extra drift layer N minus. So by inserting this extra drift layer N minus, okay, okay, now it can withstand high voltage. Why? Because since I will write breakdown voltage, breakdown voltage is inversely proportional to doping density. Breakdown voltage is inversely proportional to doping density. Okay, breakdown voltage is inversely proportional to doping density. So please understand what I'm trying to solve, sir. So here, apart from high doped, see, P plus means it is heavily doped with trivalent materials. N plus means heavily doped with pentavalent. N minus means lightly doped. See, when doping density is low, breakdown voltage is high. That means it is very difficult to break. Now you tell me an example, sir. It is easy to break. Everybody, tell me. Okay. It is easy to break balloon with high pressure or balloon with low pressure. Everyone tell me this answer. It is easy to break balloon with high pressure or balloon with low pressure. It is easy to break balloon with high pressure, na sir. Like here density. If density is large, easy to break. Low breakdown voltage only, strong field will come and it will break. But if doping density is low, to break down I require high field. High field means high voltage I have to go. That is why by inserting an extra drift layer, like lightly doped with pentavalent N minus layer. Now to break down this, I need a strong field. To break down with strong field, I need more voltage so it can withstand high voltage. So that is what. See, here it is a normal PN junction, moderately doped. But P plus N plus are heavily doped, but N minus is lightly doped. By inserting a lightly doped material, breakdown voltage has increased. So simple concepts are cross section area will allow more current and extra insulation layer will allow more voltage. So this drift layer is like extra insulation only. Yes or no? This drift layer is like extra insulation only. Okay. But you remember here also, here also you remember how many junction? There is only junction J1. Here also how many junction? Only one junction, please. Don't say this is junction. This is not a junction. This is in fact N plus N minus is only same material. Na? Junction is always between P and N. So here also there is only one junction. That is why this is also diode, this is also diode. Okay, both are diodes only. This is also a diode, that PN junction, and this is also diode with PN junction. This cannot be junction. Only difference is it is lightly doped and heavily doped. Okay, that is a basic difference you have to understand. Now, yes, now based on this, suppose I say in any application, okay, I will write a note. So I am writing a note that yes, most of our applications, yes, most of our applications are designed, okay, most of our applications are designed to work for constant rated voltage. Okay, most of our applications are designed to work for constant rated voltage, but current through them, okay, current through them depends upon loading level, load. Please understand. Okay, most of our applications are designed to work for constant rated voltage, but current through them depends upon load. Now, what is the meaning of current through them depends upon load? So load means current. Always remember, technically load means current. Suppose you see in your house, all systems are parallel now. Okay, like switch 1, light 1, switch 2, light 2, switch 3, light 3. So in our domestic supply, all are parallel. Like this is the supply voltage and all are parallel. Okay, all are parallel. Lights are parallel. Now suppose let us say, to understand this, everybody let us understand this like this. Suppose I take this as 1 volt and all the lights are only 1 ohm, for example. Okay, suppose I give 1 volt and all the lights are 1 ohm. Suppose you turn on first light. If you turn on first light, everybody, if you turn on first light, okay na? Everybody, if you turn on first light, 1 volt by 1 ohm, how much is the current? 1 ampere. Yes or no? 1 ampere. Suppose you turn on the second light. Both are parallel. 1 parallel become half. 1 parallel half means 1 by half. It becomes how much? 2 amperes. 2 amperes. Previously 1 ampere. Now another 1 ampere will add. Suppose you turn on the third bulb. 1 parallel. 1 parallel how much? 1 by 3. 1 by 1 by 3 is 3 amperes. Total 3 amperes. Okay, it is total 3 amperes. So as you are increasing the load, what is increasing? Current. That is why load means current. Okay, remember load means current. Okay, load means current. Always remember that. Now I will conclude saying that low wattage equipment versus high wattage equipment. Okay, low wattage. I am concluding, sir. Listen. What is the difference? First of all, whether it is low wattage or high wattage, in your house, voltage ratings are same. Whether it is low wattage or high wattage, voltage ratings are same, sir. Always remember. But in low wattage, okay, current is low. In high wattage, current drawn is high. But what is the design requirement? For low current, conductor cross-section area is low. But for high rating, conductor cross-section area is high. But we know R is rho L by A. R is rho L by A. Okay. Now considering the length to be same from the plug point, for the same low wattage and high wattage equipment, because resistance is inversely proportional to area, here resistance is high. Yes or no? Resistance is high. So for low wattage, resistance is high. But for high wattage, resistance is low. Resistance is low. For high wattage, resistance is low. Okay. For high wattage, resistance is low. Okay. So that is a simple thumb rule, sir. So in your house, if suppose two bulbs are given, you measure the resistance. Whichever bulb has low resistance, that is high wattage. Suppose you give me two motors, you give me. I will take the armature resistance. If the armature resistance of any motor is less, that is high wattage. So like example, let us say there are 220 volt DC motor. DC motors are there. Let us say 220 volt DC motor. Okay, where motor 1 armature resistance is 1 ohm, and for motor 2 armature resistance is 0.2 ohm. So which is high wattage? Which is high wattage or high horsepower? Answer is yes. Here armature resistance is low. Armature resistance is low, but voltage is same. Armature resistance low means thick wire. Thick wire means more current. So resistance low. So this is high horsepower. This resistance is low. So this is high horsepower. Yes or no? Low resistance, high horsepower. But here resistance is high, so low horsepower. Low horsepower. Okay. So quick review. I am giving break now. See here. First of all, I told what is ratings. Okay. Yes, I told first of all what is ratings. Ratings represent maximum permissible safe values for continuous operation. Okay. How to increase voltage rating, insulation. How to increase current rating, conductor cross area. Diode example also same. Thick area, more current. Extra layer like insulation, more voltage. Because breakdown voltage is inversely proportional to doping density. Load means current. Always remember, load means current. Okay, now. Then low wattage will have high resistance and high wattage will have low resistance. So I'm giving a break, but question is, now here I'm connecting two incandescent bulbs. See here, sir. I'm connecting two incandescent. Incandescent bulbs means tungsten filament lamps. Tungsten filament lamps are like purely resistors. Okay. Yes, I'm connecting two incandescent bulb. This is 40 watt, 60 watt. Okay. Okay, first I will take series connection. Everybody listen, parallel I will take first, then I will come to series. IES objective. So here I am taking two incandescent bulbs. First I will connect them in parallel. Okay, na? First I will connect them in parallel. Tungsten filament lamps. Here also I am taking them parallel. Okay, this is 40 watt, this is 60 watt. Okay, I am giving total voltage V rated. Okay, so question is which glows brighter? Second question is total power absorbed. Total power absorbed. Okay, total power absorbed. Similarly, this is gate question. This is gate question I'm asking. Okay, gate question. Now I'll connect the same bulbs in series. I will connect the same bulbs in series. Of course, these are incandescent. Incandescent means tungsten filament, purely resistive loads. Please understand, these are like purely resistive loads. That is why I'm showing like small resistors. Purely resistors. So this is again 40 watt, 60 watt. Okay, 40 watt, 60 watt. Okay, and I am giving total voltage V rated. Total voltage V rated. Okay, again here, glows brighter, which glows brighter. Total power absorbed. Total power absorbed. Okay, now please understand. Total power absorbed. Okay, everybody should understand. Okay, please understand everybody. Okay. So I'm giving two questions. We'll continue after the break. In the first case, there are two incandescent tungsten filament, means purely resistive here. 40 watt, 60 watt connected across rated supply voltage, which flows brighter and total power consumed. Second case, two incandescent bulbs. Okay, tungsten filament purely resistive connected in series 40, 60, but connected together to the rated supply voltage in the house, which flows brighter and total power consumed. So now it is 8:45, 9:15 we will come back. Okay, everyone take a break. 9:15 we will come back. Yes, everybody, please come back. Still some 10 to 15 students yet to join. Please come back, everybody. Who is Anusha? Raise your hand. Anusha K. Anusha K, please raise your hand. Anusha, see, active power, reactive power, that concepts will come in AC steady state, but of course, active power is the conservable part or convertible part. So power rating means active power only, okay? But this classification will come in AC steady state. But right now I am discussing more DC basics where only resistance is considered. That is why here also it is real power P only. And even in AC steady state or even power system machine, we call active power or real power. And that only we express in horsepower, etc. Okay? So it is active power only. Some students are saying noise is coming. It is your earphone problem, please. We are using noise cancellation techniques and mic is not moving here. Maybe your earphones are not good. Buy earphones which are having noise cancellation techniques. There are some earphones which is costing around 1,000 rupees and above, which have internal noise cancellation technique because these sound systems are very sensitive to use. So some students who are saying noise is coming, and again that anonymous attendee. Who is anonymous attendee? Raise your hand. Who is anonymous attendee? Please raise your hand. This anonymous attendee, please raise your hand. Anonymous attendee, who is it? Please raise your hand. And his timings, you see, system timings are 9:17 p.m., 9:12 p.m. What is the system timing you are maintaining? Okay, everybody. So let us first understand the IES objective here. Everybody look here. See here I gave two incandescent bulbs. That means tungsten filament lamps connected in parallel. Okay. Yes. First of all, out of these two, which is called rated operation, which is called underrated, which is called overrated. Now, what is the meaning? See here, whatever may be the power rating of the bulb, but each bulb in India would have been designed for 220 volts only now. Yes or no? Whether you buy any bulb of any rating, 100 watts or 200 watts or 1000 watts or 10 watt. First of all, those bulbs in India are designed for 220 volts only. Okay, those bulbs in India are designed for 220 volts only. Yes or no? Those bulbs in India are designed for 220 volts only. Okay, so these two are designed for 220 and you are also giving 220. Designed for 220 and you are also giving 220 because this is parallel connection. So this is called rated operation. First of all, understand this is called rated operation. Rated operation. But what about this? Here, both bulbs are in series and you are giving total 220. That means each bulb is designed for 220 volts separately, but together in series you are giving 220. Okay, each bulb is designed for 220 volts and 220 volts in separately, but together in series you are giving 220. So the voltage drops will be less than 220, na? Yes, each bulb is designed for 220, but together in series you are giving 220. So the voltages across them will be less than the rated values. So this is called underrated operation. Underrated operation. And this is called rated operation. Why this is called rated operation? Yes, why? Because each bulb is designed for 220 and you're also giving 220. Now in the left side IES bit it is direct. Why it is direct? Because it is rated operation. Yes. Now in parallel system, first of all, voltage is same. Okay, in a parallel system, first of all, voltage is equal across both the elements. Okay, don't see voltage now. But I told you the concept. See from the previous slide, what I told, low wattage will have high resistance and high wattage will have low resistance. So same concept here, low wattage bulb. So this resistance will be high. Okay, na? This is low wattage, so resistance will be high. And this is high wattage, so this resistance will be low. Okay, now for the same voltage, here resistance high means this current is less. Now for same voltage, this resistance is low means current is high. Current is high. So first of all, in parallel system, voltage is same. But low wattage will have high resistance in design. High wattage will have low resistance in design. Now for the same voltage, high resistance means less current. And for the same voltage, less resistance means more current. Now which bulb will have more I square R product? Just tell me which bulb will have more I square R product. I square R product will be more for 60 watt. So 60 watt will glow brighter. Okay, even in our domestic system, sir, yes, everybody, even in our domestic supply system, high wattage will be brighter, low wattage will be dim. Obviously true, high wattage will be brighter, low wattage will be dim. So that way 60 watt is brighter. Now total power absorbed, because it is rated operation. Since it is rated operation, so directly total power is P1 plus P2, both are rated, just Kelligan's theorem, total power absorbed. That is 40 watt plus 60 watt. Okay, together this is 100 watt. Together this is 100 watt. Okay, together this is 100 watt. Okay, na? 40 watt, 60 watt. Together this is 100 watt. Okay, na? So please understand that. Okay, so left problem IES bit is a straightforward bit. Out of these two, na sir, voltages are equal in parallel connection. But low wattage will have high resistance, high wattage will have low resistance. High resistance will draw less current, low resistance will draw more current. I square R product, if you take any numerical value also, I square R product, yes, I square R product will be more for 60. So 60 watt is brighter. Okay, na? Now total power absorbed here, because both are rated operation, just add them. Now right side is very interesting, sir. Right side. First of all, here both are in series. Now here when both are in series, what is equal? Current is equal. So current is equal. Now don't bring current and confuse. But again, low wattage will have high resistance and high wattage will have low resistance. Now for the same current, see for the same current here, high resistance means this voltage drop is high. For the same current, high resistance means this voltage drop is high. And for the same current, low resistance means this voltage drop is low. Okay, na? For the same current, high resistance means this voltage drop is high. And for the same current, low resistance means this low voltage drop is low. Okay, so now which bulb will have greater V square by R product? Which bulb will have greater V square by R product? V square by R will be greater for 40 watt only. So 40 watt is glowing brighter here. 40 watt is glowing. But here, how to calculate total power absorbed? Now listen, how to calculate total power absorbed? This is very interesting. You cannot add them here because they are underrated operation, sir. Underrated means both are dim together, but in that which is slightly brighter, 40 watt. Here you cannot add them because it is not rated operation. Then what to do? Now to do this problem, we should consider, a concept called, consider a concept called working resistance or designed resistance. Okay, R designed. Okay, now what is R designed? It is V rated square by P rated. V rated square by P rated ohms. This is the concept called, designed resistance or working resistance. Okay, this is the concept called what? Designed resistance or working resistance. Now I'll give an example first. I'll give an example to understand. See, example to understand this formula. Suppose in India, there is an incandescent bulb of 220 volt and 40 watt. Okay. Now when it is off, let us say the off-state resistance or cold resistance. Okay, the off-state resistance or cold resistance is, okay, let us say 20 ohms. By using multimeter, I checked it. By using multimeter. This is a practical value I'm giving, sir. So in India, I took a 220 volt 40 watt incandescent bulb. Incandescent. Okay. Incandescent bulb. Okay. I took a 220 volt 40 watt incandescent bulb. Okay. Now under off state, yes, under off state, its cold resistance is 20 ohms. Under off state, its cold resistance is 20 ohms. Now if I measure current, I is V by R cold. If I do that, V is how much? 220. R cold is how much? 20. This is how much? 11 amperes. This is how much? 11 amperes. But is really 11 amperes correct? Wrong, wrong. Array, how can a small bulb in your house which is 40 watt can draw 11 amperes? Array, fuse capacity in your house is hardly 5 amperes. Please understand this. Fuse capacity in your house itself is hardly 5 amperes. Okay, or maximum 10 amperes. Now the small 40 watt bulb, if it really draw 11 amperes, your fuse will blow off. That is why this is wrong value. This is wrong value. So what to do then? Now we should consider. So we should consider what design resistance. We should consider the above formula R hot. R hot. I will write R hot resistance or R design resistance. We call it as R designed. Okay. R designed resistance I will call. Okay. Or R designed. Now what is R designed? Yes, it is V rated square by P rated. So it is designed for 220 V rated square. P rated is how much? 40. Okay. It is designed for V rated square by P rated. Okay. This if you calculate. Okay. This if you calculate, you are getting approximately 1210 ohm. Okay. You will get approximately 1210. Okay. 1210 ohm. 1210 ohms. You will get something like this 1210 ohms. Then if I calculate I is V by R hot. I is V by R hot. V is how much? 220. Hot is how much? 1210. Okay, 1210. Okay, which is approximately 180 milliampere. 180 milliampere is absolutely correct. This is absolutely correct. Absolutely correct. So first everyone see this example. I'm explaining again. Everyone see this example. Okay, everybody, now I will explain again. See, you go through, see, in this first problem, it was parallel operation, rated operation, sir. In rated operation, no confusion. Okay, like here also, low wattage, high resistance, high wattage, low resistance, but in parallel, voltage is same, but currents are different. Then high wattage will draw more current. So I square R product is greater for 60, so 60 is brighter. And total power absorbed is adding them because it is rated operation. But in right side, it is underrated operation. Why? Both bulbs are separately designed for 220, but together you are giving 220 in series. So definitely the voltage drops will be less than 220. Nah? So it is called underrated. So in that case, what to do? Yes, first again, low wattage, high resistance, high wattage, low resistance. But because it is series, high resistance will have more voltage drop, low resistance will have less voltage drop. So automatically V square by R product. Power is V square by R product will be greater for 40. So 40 is better. Now total power absorbed, how to do? Now you cannot add. Now to do that, before I do that, first I am teaching a concept called design resistance. Here I am demonstrating that. Now normally when the bulb is off, with multimeter I got 20 ohms, and with that I calculated current which has no significance because that is a wrong answer. So what resistance we should consider, working resistance or design resistance? So if I consider the design resistance, then that is correct, and with that I got correct answer. So now why I am teaching this? Now let us apply that working resistance concept. That means really in our house now, sir, the moment you turn on, the incandescent bulbs will reach 2700 Kelvin in few milliseconds. And in that milliseconds, the temperature will be so high. That is why the filament resistance will reach almost 210 ohms. We know that resistance is proportional to temperature in metals, tungsten. So what happened? When it was off, 20 ohms in room temperature. When it is on, in 2000 Kelvin, it has reached 1210. So which happens in no time. All this happens in no time. This all happens in how much time, sir? Negligible time it happens. Please understand. Okay. So working resistance we should consider. So now let us apply here. Now this gate problem, yes, this gate problem, everybody, this gate problem I will apply working resistance. Okay, this gate problem I am applying working resistance. So now both are series now. So here total power absorbed. Now listen here. Total power absorbed is V rated square by total resistance. That is R1 plus R2. Yes or no? Why I wrote like this? Total V rated square by both resistance in series now. So I wrote like R1 plus R2. That is power is V square by R total. Okay now. But what resistance we should consider? Working resistance only. So this R1 will be V rated square by P1, and this R2 will be V rated square by P2. This V rated square will be same because in India, whether you design 40 watt, 100 watt, 1000 watt bulb, that rated voltage is 220 always. So here if you apply this V rated square by, here if you take V rated square, this is 1 by P1 plus 1 by P2. Okay. Now you remove this. Now you remove this. So this power will be P1 P2 by P1 plus P2. Yes, this is the formula. Now let us apply here. So our problem, this P total will be, now what are the power ratings here? That is 40 into 60 by 40 plus 60 watt. That is 24 watts only, 24 watts only. So together the bulbs are consuming hardly 24 watts. That is why it's called underrated operation. Together the bulbs are hardly consuming 24 watts. Both are overall dim, but in that which is brighter, 40 watts is brighter. Okay. So to understand this problem like this, sir, we consider this design resistance. That problem I kept here. See, these formulas are important. So that working resistances are V rated square by P1, V rated square by P2. That is a very, very interesting concept. Okay, remember such thing. Now I'm giving a very interesting gate question. Okay, everybody should answer this. Okay, I'm giving a very, very interesting gate questions, and I want everyone to answer this. Okay, now see this questions carefully. There are three bulbs here. Okay, there are three types of bulbs of different ratings here. Okay, now there are three types of bulbs. Okay, this is 12 volt. This is bulb type A. This is bulb of type B. This is bulb of type C. And this is 15 ampere fuse. Okay, now type A bulb. See, type A bulb ratings are 12 volt, 12 watt. Then type B bulb ratings are 12 volt, 24 watt. Then type C bulbs ratings are, okay, 24 volt, 24 watt. Okay, 24 volts, 24 watts. Okay. Now my question is, okay, now my question is, how many extra type B bulbs? Okay. How many extra type B bulbs? Okay, can be connected to supply, okay, without blowing off fuse, without blowing off the fuse. You understand this? Everybody should understand this. Okay, everybody should understand. See, there are three incandescent bulbs. There are three incandescent bulbs of dissimilar ratings. That is the problem here. Type A bulb is 12 volt 12 watt. Type B bulb is 12 volt 24 watt. Type C bulb is 12 24 volts and 24 watts. And all are connected in parallel. And remaining bulbs also you are connecting in parallel. That is the meaning there. It is understood. And the fuse capacity is how much? For 15 amperes. What is the meaning of 15 ampere fuse? See, the meaning of 15 ampere fuse is if the fuse current reaches 15 or greater than 15, it will blow. If the fuse current reaches 15 or greater than 15, it will blow. Okay, but until 14.999 it will survive. Until 14.999 it will survive. Okay, but if once it reaches 15 or greater than 15, it will burn. So how many extra type B bulbs can be connected to the supply? Of course, they are parallel without blowing off the fuse. Shall everyone do it? Yes, everybody. Yes, very good. I'm getting definitely good answers. I'm very good. See, now here, everybody, these bulbs are dissimilar rating. These bulbs are dissimilar rating. Okay, na? So whenever you see such dissimilar rated bulbs, na sir, better use this design resistance, which I told you. Okay, now convert this problem into design resistance. Now because these are the bulb ratings, see, first I will convert this into design resistance. Like I will do something like this. See, same fuse, which is 15 amperes, and the working voltage here is how much? Yes, 12 volt. Now, what is the design resistance for bulb A? V rated square by P rated. See, these ratings are not this supply. Supply is our working value, but this is the design value. Please understand, these are our working value, but this is the design value. So here, V rated square by P rated. So V rated square 12 by P rated. So this is also 12. Okay, now this is 12 ohms. Okay, and fuse is of course 15 amperes. Similarly, what about this bulb B? V rated square by P rated? This is 6 ohms. Okay, this is clearly 6 ohms. And whatever bulb C, V rated square by P rated, this is 24 ohms. This is 20. Okay, that means already how much current is flowing through the fuse? This is 12 by 12, 1 ampere. This is 12 by 6, 2 ampere. And this is 12 by 24, half ampere. That means already a current of 3 by 3.5. 3.5 means 7 by 2 amperes is flowing already in the fuse. So already in the fuse, how much current is flowing? 3.5. So extra current allowed by the fuse. Allowed by fuse is how much? By fuse is how much? Strictly less than 15 minus 3.5. Not equal to. You cannot put equal to. Equal to means it will touch 15. Then it is dangerous. So strictly less than 15 minus 7 by 2. That is 3.5. That is strictly less than 23 by 2. Yes or no? Strictly less than 23 by 2. Okay. So strictly less than 23 by 2. Okay. But each bulbs B, what it told, extra bulb B na, but each bulb B carries how much current? Each bulb B is carrying how much current? 2 amperes. So n bulbs of B, each carrying 2, should be strictly less than 23 by 2. 23 by 2. Okay. So NB is strictly less than 23 by 4. Okay. It is strictly less than 23 by 4. That is the meaning. Okay. So that means NB is strictly less than 20. Strictly, you should not put equal to. Is strictly less than 23 by 4. Yes or no? Now this 23 by 4 is 5.75. So this should be strictly less than 5.75. So NB is 5 bulbs. Okay, only. So you can connect another 5 bulbs. Sixth bulb if you put, then total here itself 12 plus that will exceed, okay, 15. So it will break. So 5 bulbs only you can put. So I can connect extra 5 bulbs of type B. Without blowing off the fuse. But if I connect to the 6th bulb, then the current rating will exceed the fuse current rating and it will blow off. Okay, that is a simple meaning of this problem. Okay, everybody see here. Okay, that is the meaning. So whenever you see problems on bulbs, heaters, etc., whenever you see problems on bulbs, heaters, etc., you immediately convert into working resistance problem. Okay, you immediately convert into what? Working resistance problem and do it. Okay, that is a very simple way and easy way. Okay, na? Chalo. And with this, all basics are over, sir. Now I am starting a very major topic. So this is module 2 of chapter 1. That is passive element reduction or resistor. First, initially I will go resistor, mostly resistor reduction techniques. Okay, resistor reduction techniques. Okay, I want to show now resistor reduction techniques. Now this is very interesting. Everybody is having pen and a paper, book and a paper. Raise your hand. Everybody, see, otherwise you will not enjoy this class, sir. Now onwards it will be very interesting. Until now, all basics, definition, theory, formulas are over. Now it is more interesting, sir. Okay. So now I want everyone to put a pen, paper, whatever I'm writing, write down and try to do it. However, notes we are sharing now, sir, that is not an issue, but your working and practice is important. Okay. So now these are the questions to find equivalent resistance. So I'm giving the first problem here. So what is that you have to find? You have to find the equivalent resistance as seen by the target terminals. Okay, this is the first question. 1 ohm, 2 ohm, 3 ohm, 4 ohm, 6 ohm. I want resistance seen between these two terminals. Second question. Okay, second question I'm writing here again. One ohm, 2 ohm, 3 ohm, 3 ohm, and also 3 ohm. So I want the resistance seen from here. Okay, resistance seen between these two terminals. Okay. Now I'm giving, yes, I'm giving another question to find what is RAB. What is RAB? Okay. Now I'm giving another question. Find what is RAB. Okay, na? I need RAB. Now this is 3 ohm, this is 6 ohm, this is 2 ohm, this is 2. Okay, I need RAB. Okay, I need RAB. Chalo, these three problems do it. I'm giving only 2 minutes. Quick, sir, 2 minutes only. You should do it. Okay, now everybody should see now. Chalo everybody. See, we are doing now register reduction techniques. See, reduction is the main heart of circuit theory because lumped parameters we are learning. So in my subject matter, it all starts with lumped parameters. So simplifying by lumping. Okay, simplifying by lumping. Lumped parameters we call. Okay, now in that regard, see, first of all, this first network is a bridge network. It is a bridge structure because here no two elements are either series nor parallel. This 4 ohms is coming as a cross arm or central arm, due to which no two elements are either series nor parallel. So this is famously known as bridge structure. Even the second one is also called bridge network. Okay, so this 4 ohm is called the cross arm or central arm. Okay, na? Now, actually, in such case, because no two elements are either series nor parallel, you can convert star to delta or delta to star. But luckily, here the bridge is balanced. Why? The product of opposite arms, see, 1 into 6 is equal to 2 into 3. 1 into 6, 6 is equal to 2 into 3. So for this case, I will write, bridge is balanced. Bridge is balanced. Okay, na? Bridge is balanced. When bridge is balanced, please understand, when bridge is balanced, everybody, yes, now we can remove this cross arm. What is the reason? Because in a balanced bridge, when I give energy, the potential of this point equal to potential of this point. When potentials are equal, potential difference zero, current cannot flow here. Current cannot flow. So current cannot flow. So in a balanced bridge, if you give any voltage, the potential of this point equal to potential of this point with respect to any other third point. When these 2 points are at same potential, potential difference is zero. Current cannot flow through 4. Okay, that is why 1 into 6 is equal to 2 into 3 is called bridge balanced. Then you can neglect 4. Then if you once neglect 4, see, please understand, if you once neglect 4, then what will be the answer? This 4 is in parallel to 8. Because once you remove this, see, once you remove this 4, because current is not flowing, I will treat it like open circuit. So once you remove this 3 plus 1, 4 is in parallel to 8. Yes or no? So there is nothing but 32 by 12. That is 8 by 3 ohms. That is the first answer. 8 by 3 ohms. Now, second case is very interesting. Sir, in the second case, here in the second case, bridge is not balanced because 1 into 3 is not equal to 2 into 3. Unbalanced bridge. This is an unbalanced bridge. So here, I will write here, this is unbalanced. Unbalanced bridge. Now, in an unbalanced bridge, when I give any voltage, the potential of this point is different potential to this point. So current will flow through 3. That means even 3 ohms must be considered in reduction. In a balanced bridge, what happens? These 2 points are at same potential, current cannot flow, so I can neglect 4 ohms. But in an unbalanced bridge, these 2 points potential difference exists, so current will flow through 3 ohms also. Now in that case, then better to do only star to delta or delta to star. I will pick up any one of the delta and convert into star. Okay, I will pick up any one of the delta and convert into star. But better down delta is easy, Nasa, because all are 333 ohms. Yes, this 333 ohms, if I convert into star, the equivalent resistance become 1 ohm, 1 ohm, and 1 ohm. Okay, na? So I will convert. See what I did? I will convert. Okay, this 333 ohm, one of the delta into star. Then this network becomes something like this. You see now, this network becomes something like this. Okay, because I converted into star, it becomes like this. See here. So what is happening now? This is 1 ohm, 2 ohm, they are like this. But this 333 I converted into 1, 1, and 1. So this answer will be 1 plus 2 in parallel to 3. 2 in parallel to 3. So this is 1 plus 6 by 5. Answer is 11 by 5 ohms. 11 by 5 ohms. 11 by 5 ohms. Okay, 11 by 5 ohms. Okay, certainly answer is 11 by 5 ohms. Okay, na? Sure. Now I am going to the next model. Yes, I am going to the next model, everybody. Now here I want resistance between AB. Now resistance is passive property. Okay, na? Resistance is passive bilateral property. Then remove the active element. Okay. Now resistance is passive bilateral property. So remove the active element. Who is the active element? Ideal voltage source. So active element is ideal voltage source. Na? So I will short it. Active element is ideal voltage source. I will short it. Because ideal voltage source internal resistance is 0. And we are finding resistance na. So its resistance is 0. So I will short it. So this is what I am trying to do. Okay, na? This is A and this is B. Okay, this is 3 ohm, this is 2 ohm, this is 6 ohms, and this is 2 ohms. Okay, everybody watch this. So resistance is passive bilateral property. So remove the active elements. Which is the active element here? 10 volts. So I removed it. I shorted it. Okay, this became like this. Now I will further simplify. See this short circuit wire which is coming from here to here. This short circuit wire which is coming from here to here. I will connect like this. Yes, I will connect like this. Meaning is same. Na? If I connect like this or even directly like this, it is the same meaning. and this A I will bend here, and this B I will bend here. Now I'll remove the unnecessary part. Okay, I'll remove the unnecessary part. Okay, this I directly wrote there, and this A I bend it that side. Okay, and this B also I bend it this. Now clearly if you see, now clearly if you see, this is a single node. Yes or no? This is a single node. This is a single node. Now between this node and this node, these two are parallel. These two are parallel. Again between this node and this node, these two are also parallel. These two are also parallel. So 3 and 6 parallel 2 and 2 and 2 parallel 1. So final answer is 2 plus 1. It is 3 ohms. It is 3 ohms. Okay, now final answer is 2 plus 1. It is how much? 3 ohms. Again, see everyone see the three models. I am giving you time. See the three models. I will explain again. So first two problems are bridge structures. But in the first problem, it is a balanced bridge where product of opposite arms are equal. That is why current will not flow through 4. I removed it, then 4 in parallel to it. But second is an unbalanced bridge. So we have to compulsory convert one of the delta into star or star into delta. So I converted the easy part of delta 333 into star, corresponding value become 111. Then again series parallel. Now the third is about finding resistance. So resistance is passive electric property, so remove the active element. Active element here is a voltage source, so I remove it, short it. Then this becomes 3 ohms. Okay, na? Chalo, I am giving the next set of problems. Everybody, yes, I am giving the next set of problems. I want you to write again. Now again, sir. What is this resistance RXY? This is now 5 ampere, 2 ohm, okay, X, Y, 1 ohm, O, okay, 2 ohm, 4. Okay, chalo, I need this RXY. Okay, I need RXY. Now another question, again RAB, this time more interesting. $20 6 ohm, Okay, I need RAB. Chalo, do these problems immediately, everybody. Do these two problems. Here RXY, here RAB. Everyone, 1 minute only. Left side RXY, right side RAB. Yes, everybody, are you doing? See, this is the style of these subjects. Are now I told na sir, once numericals come, I need your lot of hard work. This subject is just not theory subject. So we have to practice together. Chalo, now listen. Left problem. See, in the left side problem, I need RXY. Again, resistance represents what? Passive property. So remove the active element. Active element here is what? Current source. So if I remove that, see, watch. This will become something like this. Okay, na? If I remove current source, how it will become, sir? It will become something like this, because current source internal resistance is infinity. Okay, and X I am bending this side, Y I am bending this side. Current source internal resistance is infinity, so I open this. Now this 2 ohms is a dummy element, waste. Why? Because it is open circuit. Okay, open circuited, and you are working between what? You are working between X and Y. So when you are working between X and Y, this current source is open. When your current source open, this 2 ohms is waste, na? 2 ohms is wasted because you are working between X and Y. So this you can remove. Okay, in fact, you can remove this. Now it is very simple that, yes, it is very simple that this is 1 plus 2, 3 is in parallel to 2 plus 4, 6. 3 in parallel to 6 is 18 by 9, 2 ohms. So the final answer is 2 ohms. Okay, na? Similarly, right side you see. Now this is interesting. Now right side I need RAB, but this time it is a voltage source with resistance again. So voltage source I will short it. Yes, voltage source I will short it. Okay, and rest of the network I am writing like this. Okay, rest of the network I am writing like this. Okay, now this is interesting. Okay, so this is 6 ohms. Voltage source is shorted. This is A and this is B, and this is now 1 ohm, 6 ohm, 6 ohm, and 4 ohm. Okay, 1 ohm, 6 ohm, 6 ohm, and 4 ohm. Now this 6 ohms connected between this and this 6 ohm connected between this and this, I am connecting like this. Okay, this 6 ohm connecting this between this and this, I am writing like this. This A I am bending here. Okay, this 6 ohms I am writing here. Where this 6 ohm came from, this wire only, sir. This wire I am writing directly here. Okay, na? That is what I did. So now I am removing this confusion. Okay, na? Chalo. Now this A I am bending left side and B I am bending right side. Okay, same terminals. Okay, na? Chalo. Now see, sir, this becomes a bridge structure. Now this is a bridge structure. Okay, now this is a bridge structure because this 6 ohms is there now. Cross arm element is there. But is the bridge balanced? But is the bridge balanced? No, no, sir. Bridge is not balanced because 1 into 6. Yes, 1 into 6 is not equal to 4 into 6. Bridge is not balanced. Please understand that. Yes, bridge is not balanced. That you should understand. That 1 into 6 is not equal to 4 into 6. So now I will convert this delta into star. Okay, I will convert this delta into star. So all 666 ohms in delta corresponding value in star become 2 ohm, 2 ohm, and 2 ohm. Okay, na? 2 ohm, 2 ohm, and 2 ohm. So now I can further simplify. Yes, now I will further simplify. See, this is already 1 ohm here and 4 ohm here. Now I converted into all 2, 2, 2. Okay, because 6, 6 become 2, 2, and 2 in star. Okay, and this is B and this is A. So this is already 1 ohm and 4 ohm, but this become 2, 2, and 2. Now very simple, sir. See, this 1 plus 2 become 3. This 2 plus 4 become 6. So 3 in parallel to 6 plus 2. So 2 plus 3 in parallel to 6. That is 2 plus 3 in parallel to 6 is again 18 by 9. 2. 2 plus 2. Answer is 4 ohms. Answer is 4 ohms. Answer is 4 ohms. Okay, na? Answer is 4 ohms. Okay. So, sir, I am giving the next set of questions. Okay. After that, I am giving the next set of questions here again. Okay. After that, I am giving next set of questions. Okay. Here again, this is an IES objective. What is RAB? Okay. What is RAB? A is here, B is here. All are 1 ohm. 1 ohm. 1 ohm. 1 ohm. 1 ohm. What is RAB? Okay, now what is RAB? Okay, I want everyone to understand what is RAB, and this is IES objective again. Okay, here also what is RAB? Here also what is RAB? Okay, IES objective, what is RAB? I want the equivalent resistance as seen by the target terminals. So these are my target terminals A and B. Okay. Now I want again the resistance here, like 1 ohm. These are all 2 ohms. This is something like 3 ohms and this is 4 ohms. So these 2 bits everyone should do. Both are IES objective. First question also what is RAB, second question also what is RAB. Okay. Okay, everybody. Yes, some students are really doing, sir. Now see the left one. See, actually left one looks like this, but it is a balance bridge only. So what I will do node shifting technique, sir. See, left side is looking like this, but it is a balance bridge only, sir. See, I will do like this. Now this junction is A, so this junction is automatically A, and this junction is automatically B. Now let this be X and let this be Y. So I will rewrite like this. See, A, B, X, Y. I'm just shifting the nodes. See, A to X 1 ohm. Okay, A to X 1 ohm. A to Y 1 ohm. Okay, A to Y 1 ohm. Then B to Y 1 ohm. Okay, B to Y 1 ohm. B to X 1 ohm. So B to X 1 ohm. Then X to Y 1 ohm. X to Y 1 ohm. And you are looking between A and B. So now you are looking between A and B. Now balance bridge. Current cannot flow. So 2 in parallel to 2. Answer is 1 ohm. 2 in parallel to answer is 1 ohm. Okay, na? Now let us come to the right side problem. In the right side problem again, it is a planar network only. It is looking confused. So again, I will do this node shifting. I'm not talking bridge yet, but first let me do node shifting. See, this is A, this is B. Okay. Now let this be X and let this be Y, and let this be some U and let this be some W. See how I am writing now. Everybody watch this. See, A and B are my target terminals. Okay. Nearer to A is X. Okay. Nearer to A is X. Okay, nearer to B is Y. Okay, nearer to B is Y. Then this U and W, I will shift lines. See, U and W, I will shift lines. So now see, everybody now see. Now A to X1, okay, A to X1 ohm. Then X to U 2 ohms, X to U 2 ohms. Okay, okay. Then again U to W 3 ohms, U to W 3 ohms. Okay. Then again W to Y 2 ohms, W to Y 2 ohms. Okay. Then again, Y to B 4 ohms. Okay, Y to B 4 ohms. Okay. Then again, X to W2. Okay, X to W2. Okay. And then Y to U2. Okay, Y to U is also. Hello, sir. Now this part is balance bridge, na? Yes, this part is balance bridge. Current cannot flow here. So this RAB will be, okay, this is 1, but this 4 in parallel to 4. 2 plus 2, 4 in parallel to 4 now, because this is 3 ohms is not working balance bridge. Open it. So 2 plus 2, 4, 2 plus 2, 4. 4 in parallel to 4 plus another 4. So it is 1 plus 2 plus 4. Answer is 7 ohms. Answer is 7 ohms. See, in both cases, I shifted the nodes. See, in both cases, what I did, I shifted the nodes. Okay, I shifted the nodes. That is what I did. In both cases, I did not do anything great. I just shifted the nodes. Node shifting technique we call. Okay, na? Now I'm giving next set of problems, sir. I'm giving next set of problems. This is a gate bit, sir. Gate 1 mark. Okay, so this is gate bit. 3 ohm, 3 ohm, 3 ohm. I want the resistance. Okay, 3 ohm, 3 ohm, 3 ohm, and I want the resistance. Okay, now this is IES objective. IES objective. What is current IX? What is current IX? What is current IX? Okay, what is current IX? Okay, now this is total 12 ohm, 12 volt. This is 3 ohm, 3 ohm, 3 ohm. Now I want this current IX. Chalo, I want this current IX in this branch. Okay. Chalo, everybody do these two. IES bit and one is gate bit. In the first gate bit, I want the resistance in terminals, and here I want the current IX. Should everyone do it immediately? Everyone do it immediately. Okay, everybody. Chalo, everybody listen now. Yes, if you observe now, what is the resistance in here? What is the resistance in here? Everybody should understand. See, it looks confusing now, sir. I do node shifting. Now listen, what I will do node shifting. See, this is A. Now this junction is A. Same wire, this is also A. Now this is B. This junction is B. Same wire, this is also B. So finally there are only two terminals, sir. Okay. Finally there are how many terminals? Only two terminals. Okay, now like A and B. A and B only. One A to B, 3. Okay. One A to B, 3 ohms. Another A to B is also 3. Yes or no? Yes, 3. And another A to B is also 3. Another 8 is also. So 3 parallel. Answer is 1 ohm. Answer is 1 ohm. All are parallel. Yes, all are parallel, please. Okay. Now look at this. I need current Ix. Now here also it is looking confused. So I do node shifting. Let this be A. So this junction is also A. But same wire here now, sir. This is also A. Now this is B. This is also B. Same wire. This is also B. So again between AB only. Chalo, again between A, S, B. Okay. Only you are talking. One A to B, 3. Yes, one A to B, 3. Okay. Another A to B, 3. This AB is also 3. This AB is also 3. Okay. Now we are giving voltage between AB where A is positive with respect to B, which is 12 volts. Okay. So now we are giving voltage between AB where A is positive with respect to B. Okay. So this is positive, this is negative. Now in a sync current enter first not 12 by 3. This is 4 amperes. This is also parallel 12 by 3, 4 amperes. This is also 12 by 3, 4 amperes. But he is asking current Ix. Yes, he is asking current Ix in which direction? Everybody understand. He is asking current Ix from B to A. He is asking current Ix from B to A. But actual current is going from A to B. So Ix is, yes, Ix is how much? Minus 4 amps. Ix is minus 4 amps. Okay, that is the answer. Ix is how much? Minus 4 amps. Please understand. Ix is minus 4 amps. Okay, na? Yes, it is minus 4 amps. Now I'm giving a simple gate bit 1 mark. Okay, gate bit 1 mark. Now what is R equivalent? Okay, what is R equivalent? Okay, yes, I am giving what is R equivalent. Okay, this is the problem where I am asking what is R equivalent seen here. Okay, this is some 10 volts. Okay, 2 ohm, 6 ohm, 3 ohm, 5 ohms. So what is R equivalent? I am asking. Okay, that is the first question. Okay, R equivalent. And then I will give another IES objective. So IES objective to close today's session. What is RXY? Okay, what is RXY? Okay, what is RXY? I'm giving you. This is 2 ampere, 9 kilo ohm. This is 1 kilo ohm. This is 10 kilo ohm. This is 5 volts and 2 ohm. So these are practical sources. 2 amperes, 9 kilo ohm, 5 volts, 2 ohms. And this is 1 kilo, this is 10 kilo. I want resistance between X. So everyone will do these two and stop today. So everyone try to answer them. Yes, everybody see here, I need R equivalent. Now this is a simple observation bit, sir. Left bit is an observation bit. Now, because I want resistance, yes, because I want resistance, okay, I can remove the voltage source. Yes or no, I can remove the voltage source. So if I remove the voltage source, watch this, that I'm shorting. Okay, remaining things I'm writing again. Okay, remaining things I'm writing again. Okay, now remaining things I'm writing again. Okay, this is now 3 ohm, this is 5 ohm, this is 6 ohm, this is 4 ohm, this is 2 ohm. Okay, okay, you're looking from here. Chalo, you're looking from here. Yes, you're looking from here. Yes, voltage source short, voltage source short, and you're looking from here. Now, see these 2 ohms between this node and this node, because it is same wire, I can swap these 2 ohms like this now. This is very interesting. See, between this node and this node, 2 ohms is there, sir. But this point is same point, na? Yes, this point is same point. So I can swap 2 ohms like this. Yes or no? Yes, it is same point only. Now, this is one target terminal and this is one target terminal. So if you look here, it is a balance bridge. That is a very interesting observation. You can also do star delta delta star, but it will take time. Now it is a balance bridge because 3 into 4, 12, 2 into 6, 12. So I can neglect 5. So I can neglect what? 5 can be neglected. Okay, now 5 can be neglected. So if 5 can be neglected, so if 5 can be neglected, then finally, okay, then finally this 3 plus 6, 9 is in parallel to 2 plus 4, 6. Okay, so 9 into 6 by 15. Okay, 3 2s are 3 5s are 18 by 5 is the answer. 18 by 5 is the answer. Right side is your practical sources. Now practical current source. Now listen, practical current source has large resistance in parallel. Yes, that large resistance he gave like this. Yes or no? Yes, that means it is originally 2 ampere and 9 kilo ohm modeling because practical current source has large resistance. Okay, however, this 1 kilo is there as it is. Okay, however, this 1 kilo ohm is that it is, and this 10 kilo ohm is also as it is. Okay, and this practical voltage source has small resistance in series. Yes, small resistance in series. Yes or no? These are small resistance in series. 5 volts, and this is 2 ohms. 5 volts, 2 ohms. Okay, so your practical current source has large resistance in parallel, and practical voltage source has small resistance in series. Okay, now this I can remove. Current source open. Now ideal part you can remove. Current source open and voltage source short. Chalo, voltage source short. Now if you see 9 plus 1, 10K in parallel to 10K. So this RXY will be this 10K in parallel to 10K. Okay. Yes or no? Because this 9 plus 1, 10K, 10K parallel plus 2, another 2 ohms. So 10K, 10K parallel 5000, 5K plus 2. So answer is 5002 ohms. 5000 ohms. Okay. So with this, I am closing today's session, sir. And tomorrow again we will meet. Chalo, doubt. Varsharani Patil. Varsharani Patil, what is your doubt? Varsharani Patil, what is your doubt? Okay. Varsharani, any doubt? Okay. Pratyush.
Hello, sir. Good morning, sir. Hello, sir.
Tell me.
Sir, in two questions you have given which bulb will glow higher. Sir, in case of series connection of bulbs, sir.
Tell me what is your doubt?
Sir, intensity of light depends upon the flow of current, no, sir.
Yes, of course, current is equal both ways, but voltage drop also will decide the power. Of course, that current is equal. No. Intensity of bulb does not depend upon current alone here. See, I square R is the effect, heating effect.
Yes, sir.
Though current is equal, don't say both are same because the voltage drops are different, na?
Yes, sir.
Overall power rating. That is why just by seeing voltage and current, you should not decide. Power is product of voltage and current product.
Sir, that means intensity of bulb depends upon power, sir. You can say like that, sir.
Power, yes, because resistance also heat loss. See, V and I are obeying Ohm's law mostly, but yes, in linear elements they obey the linear relation, but together product is power.
Okay, sir.
Okay.
Okay, sir. Thank you, sir.
Right. Then Jamotkar, Pranjali Jamotkar.
Hello, sir.
Tell me.
Can I ask doubt in yesterday's class?
Tell me, please.
Sir, yesterday we did that question in which number of turns was doubled and we were supposed to find the time constant.
I know. Tell me.
Sir, in that, sir, we said that number of turns are getting doubled, so length of resistance will also get doubled. But sir, if length is getting doubled, then area of that resistance should get halved.
No. That is not the meaning. See, you know kite, patang, cherka. You know.
Yes, sir.
I'm giving that example. Cherka is like a toroid. Suppose you want to fly kite height higher, so we need more length of thread, na?
Yes, sir.
That means number of turns are increasing. Thread length also will increase.
Yes.
But thread cross section area is same, na?
Okay, sir. So,
To get the double the turns, I am taking the same wire, but more turns. So length of the wire is increasing, but area I am not touching.
okay, sir. So, okay, sir.
What happens there is, I am not stretching the wire. In this case, yes, your doubt I understood. Suppose if I stretch the wire to make double turns, then I have to use your concept.
Yes, sir.
But I'm not doing like that. I'm just adding more turns for the same cross-section area.
Okay, sir. Like in that cube question, we stretched that cube.
There I gave if the cube is stretched in one direction. But here I'm just asking to increase the number of turns. Means I'm adding the wire. I'm not stretching the wire.
Okay, sir. Clear.
Understood. Very good. Doubt I understood. Anyone now? Shiva?
Good morning, sir. Sir, the number of bulbs problem, sir.
Number of?
Number of bulbs to be added. That
What
problem.
is your doubt? Tell me. What is your doubt?
Sir, we can keep that the rating as it is, and if we calculate the number of bulbs, it will be same or it will be different, sir.
See,
Like for type C bulb, we have 24 volts, but we are giving a supply of 12 volts. So if we keep the same bulb as it is, and if we calculate the number of bulbs,
it is underrated, it will glow, but it will glow dim.
Yes, sir. I have one doubt here, sir. So if the voltage is reduced, will the current like it will increase and the intensity will be matched, or it will glow dim, sir?
No, depending upon the power rating, you have to see again. See, that means originally this is a 24 volt and 24 watt. So by connecting to 12 volts, only half ampere is flowing. That means it is dim only.
Yes, sir. That's what I'm asking.
It is dim only. Okay, na?
Okay, sir.
Underrated operation. That bulb C is underrated. Bulb A and bulb B are rated operation.
Okay, sir.
Right.
Yes, sir. Clear, sir. Thank you, sir.
Pawan.
Sir, for bulb C,
Tell me what is the doubt?
sir, for bulb C, power rating is 24 watt, no, sir. If we use P is equals to VI, then the current will be 2 amperes, no, sir.
No. That is what working voltage is 20, designed is 24. That is why it is underrated. We learned the same thing previously also. It is designed for 24 volts, but you are giving only 12 volts. So it is operated underrated.
Yes, sir.
When your concept is correct, when you are giving rated voltage and rated design, then your concept applies. That is why underrated, overrated, you should never do like this, I told.
Okay, sir.
Okay?
Okay, sir.
Right. Bharat. Bharat. Sangeet.
Hello, sir.
Yeah, tell me.
Sir, I have a doubt regarding the second set of questions we did in resistance reduction technique.
Yeah, tell
The
me.
one with the current source and sir, this question.
Tell me.
In this, sir, this RXY, when we consider here, this bridge is also balanced, right? Should we consider that effect when we take RXY?
No, this is not a bridge at all. According to me, this is not a bridge at all. Okay, because see, bridge is a passive concept. If only pure passive elements are there, we call it as a bridge. Bridge arrangement is different, but bridge with resistors is different. Bridge arrangement, I can say your argument, it is a bridge arranged system, but actually there is a current source here.
Yes, sir.
And the question will define everything. Suppose the question is defining, yes, what is the resistance between X5? So resistance is purely passive property. So I will deactivate. After deactivating, we should argue the question.
Okay, sir.
Then,
Continue.
understood now. Suppose if it is purely resistance, then your argument is correct.
Okay, so suppose instead of that current source, it was just a, suppose it was just a shorted or something, then or if that whole branch 2 ohm and 5 ampere current source is not there in the first place, and they ask us to find just the bridge and XY terminals are there, then we can argue that the resistance is not there. I'm a little confused, sir.
No. If suppose instead of this 5 amperes, only 2 ohms is there. Let us say this 2 ohms is there.
Okay, sir.
Then you can write this 2 ohms here. Then it is a balance bridge. Then also you remove these 2 ohms and say this 3 is in parallel to 6.
Okay, sir. So here, since the 5 ampere current source is there, or had it been another voltage source, we couldn't use the bridge concept here.
Then that voltage source problem we did here. See, here we shorted this. Then it is not a bridge. It is a single node here. Then these two become parallel, these two become parallel. Then by shorting this also, it is not called as a bridge. It is only a simple node where, yes, these two become parallel, these two become parallel.
Okay, sir. Okay. Okay, sir. Yes.
Okay, like it depends upon what you are connecting and what is being asked there. But structure is bridge structure, yes. Arrangement is correct.
Okay, sir. Thank you.
Anil?
Sir, please tell me.
Yeah.
Sir,
Anil, tell me, Anil.
can you please explain that again, sir? KVL violations.
See, if two voltage sources are in parallel of different values, that is wrong because you cannot write a KVL. Ideal voltage of different values cannot be connected in parallel. That is what I told. Ideal voltage sources of different values cannot be connected in parallel. Like here you see here you see. Like 10 volts and 5 volts both in parallel, ideal voltage source without internal resistance, then this is a wrong concept. But if they have some internal resistance here, then it is okay.
Okay, sir.
But two ideal voltage sources cannot be connected in parallel. That is violation of KVL because you write KVL in the loop now. Minus 10 plus 5 is not 0 now.
Yes, sir.
Okay, that is the meaning.
Thank you, sir.
Right. So everybody.
One for the last question.
What's the last question?
Last one. Yeah. Resistance reduction. Here the current source has to be open circuit.
You opened it, but first equivalent circuit, current source in parallel to resistance.
Okay.
समझ गया? Now open किया दिया. Our voltage source in series to small resistance practical. But resistance is being asked now, so internal resistance must be considered.
Yeah.
Okay?
Okay.
Okay, right. So again, everybody tomorrow morning 7 o'clock.